All right, now let's try to discuss about handling large blobs. This is a small pattern, so we'll just try to get this quickly done. So here basically we know that databases are not meant to store bigger files like let's say like greater than 10 MB files. Usually if a smaller files, if you try to store as a blob in DB row and try to query, that's fine. But as file keeps on growing its size, like greater than 10 MB files, they're not meant for the storing of this kind of things. So what is the place to store, and how can we optimize those things and all is the pattern. So ideally we try to see in the Insta, YouTube, or Dropbox, and all these platforms that are mostly related to the files. These are the patterns that will try to fit in systems of that kind. So let's try to understand. So basically first, in the first place, why do we need that blob storage? So like I mentioned, so these are not meant for the binary objects. Are meant for structural data and queries, like properly having strongly typed columns and all, and anything besides greater than 10 MB and NoSQL. So blob storage is the way for us to go ahead and store it. So first, the problem is we don't want to act the file uploads through our servers, because every byte that gets routed through our servers, they add a latency and cost, and it really adds no value to the end users except the bad user experience. So let's say like we wanted to transfer 2 GB of the file. Every time that goes through our API gateway and hits the server, and then we try to store this in blob storage. So here the servers are just like the transport layer, and they are like dumb pipes. They even though they don't want every byte, and they touch. So here like trying to make it go through a server, like going direct tries to bring problems. Like maybe let's say like 99% is done, and it some due to network problem or so it collapsed, and so on. So it needs to start all the way again to upload, and everything should go through our server, and it needs to handle the traffic, and so no progress and all. So there'll be no progress tracking and all the status drift and all. So we need to avoid. Now how can we just keep our main servers also just out of the loop of intaking the file from the client? That is the the mindset or the thought process that should be when we are trying to handle this blobs. So for that basically here the solution is trying to make the server as the access layer instead of transfer layer. So here what we do, basically we try to give a client temporary scoped credentials, kind of so that they can use that URL to directly upload to the blob storage instead of keeping the server as the intermediate layer. So that way now we are trying to turn this server from the transfer layer to the access control layer. So that's the thing. So we send these client credentials to this client, that is that is called basically pre-signed URL, and once the client gets the pre-signed URL, it can transfer the bytes, whatever the file that it wants to send, directly to the blob storage. So that's the thing we wanted to avoid and make this server less data access as the approach. So now let's think about the simple direct upload. So it's a simple and straightforward. This server, whatever it is, this hands back our server, it hands back the pre-signed URL, and this client, what it does, it tries to put the file straight to the blob storage through this route. So the one that I just discussed, and now we are completely detaching this from the blob storage. So that's the pattern. And here this basically this request signed URL, pre-signed URL is a two-way. So this clients puts this URL to this URL, whatever we send, then the server just whatever it just tries to create with whatever the secret access key and all that we have, the env values that we try to set with local creds, and there will be no network call even to blob service and all. So this URL, what that ideally will have is basically the credential and a date and expiry and plus signature. That is what it carries, and once it sends that to the blob storage, then it will have its the secret key that we used to send that URL with the signature, and it will verify and it will try to take that file and upload it to this blob storage. So and we can control, basically it will have like content length range and maximum per that URL, and also basically that's a way to avoid malicious actors to upload like let's say 100 GB 1 TB or so. Instead of that, we can restrict them to like 10 MB or let's say like 20 MB or so per this content length range, and also the type. And we like this we can restrict not to upload video for the blob that is created to accept the images. So this is a simple direct upload. That's the simple process, and the download as well. So basically signed URLs give the temporary read access, and this will try to serve from the CDN, like trying to provide an option for the end users which is frequently accessed, and they can directly try to download from the CDN edges near that user. So simple. Here as well, client gets this signed URL and then downloads directly. This we have this here two ways of signing that thing, blob signatures. So those are like basically S3 pre-signed. So this will be completely validated by the storage itself with the secret access key whatever we had created from that respective cloud. And the CDN signatures, basically this CloudFront that I was talking about, CDNs, so they are usually validated at the edge using the public and private key cryptography. And basically we the client holds the private key and signs the URL, and the CDN has the corresponding not the client but our server, and the CDN has this corresponding public key, and it will try to validate that signatures at the edge locations and all. So that's how like we facilitate even the download without our server being in the picture. And now let's talk about the resumable uploads for large files. So that's a very important feature, and also it's like pretty standard these days. Any application which involves file intake by default all the cloud offers this. So so idea is to try to split big files into smaller chunks. So for example, AWS allows us to upload in the 5 MB chunks, and instead of trying to upload maybe 5 GB or 10 GB at a time. So the problem there, just imagine, let's say we have like 10 GB video and like let's say 5 GB and we have some network speed of like 100 Mbps or so. So ideally it would take around 7 minutes or so to upload that complete file. Let's say in between or like at the end, like 90% or so we lost the connection, then again we need to start all the way from scratch. So that's something we do want to handle, and it's something we want to avoid that. So that is why like for example S3 if we take, it provides us the multi-part uploads where each 5 MB plus gets its own pre-signed URL. So even if let's say we have 100 parts and somewhere we lost the connection once we send the 60 parts or so, and now the client will resume from 61st part onwards instead of starting all the way from the zero. So that's this multi-part really helps us to resume from the part at which we failed, and the idea is to split into chunks and try to upload this. And basically once the 100th part is done, so and the blob storage tries to stitch into one object, and all the chunks now it's completely it's something, it assumes those chunks are not part of the blob anymore. So that is where again we need to have some lifecycle rules, like trying to clean up every 2 days or so, because storing in the blob is going to cost us money. So just to avoid, because anyhow we'll not be able to use those chunks, or we'll not be using directly, we'll try to use the one storage which it has stitched to. So that's the thing. And the progress tracking is very important when we wanted to show as the on the client side as a best user experience. Basically progress is nothing but the parts done by the total that we have. So we'll try to finish with the completion call once all the parts are uploaded, and that completion call to the blob storage, it will be like passing in all the part numbers along with the checksums for that thing, and then it will use that to stitch all of them into the single object, and then it says like now I'm no longer in charge to the chunks, and it's your responsibility to clean up or keep it. And so that's the multi-part upload usually we try to take in. And now let's try to see how do we synchronize this state. So basically we know that now the server is completely detached from the blob storage, and now how do we maintain the state synchronization between our server and the blob storage? So that is where, like, we know file lives in blob storage, and its metadata, usually the pattern is like we're trying to maintain in our DB, and so keeping them in sync is kind of like something we need to be very careful. So there might be scenarios that file is stored in the blob, but the status is not updated in our metadata DB, and it can be vice versa. There can be race conditions, that is, database might show it's completed, but the file doesn't really exist in file storage, and again vice versa. And also malicious clients might make the uploads as complete in our metadata DB, though they have not uploaded anything, and any network failures and all. So those are the problems, race conditions, orphan client, and malicious actors, and then network completions. So this basically we need to be very careful here, and that's where, like, how do we handle that state the sync once the 100% of the file is completed and uploaded in the blob storage, and how are we going to handle? So we have the concept of like event notifications. Usually blob storage really helps us to provide those event notifications, so that now instead of relying so the above problems arises when we are trying to rely on the client side. So we are relying on the client side, like, once it's done, please let us know so that we can update in our metadata DB. So instead of relying on the client, the idea here is to try to rely on the blob storage itself. So that's this idea, that is more reliable, and also that's what it's adopted mostly. So state sync, we try to adapt this event notification that blob storage provide. So this what it does, the storage itself confirms like what exists and all. And also this reconciliation idea is basically, let's say we might miss few of the blobs event notifications, or some of the rows in the DB might still stay it as a pending and all. So we might do periodic job that that catches all of this pending things, and we try to scan in the blob storage and get the status, and we can update the status. So idea is simple. The client and the API gateway server and anything related to metadata, we try to listen to this event notifications and update our row in our primary DB. The idea is simple. Storage really emits an event and upload. We update the DB row status, basically, like, it's a pending, and we have the storage key and all the those things. And once it is done, we will try to find that row with that storage key and update the status as completed. And even trying to send from the blob storage, that might fail. That's where, like, reconciliation job basically tries to help us to recheck that file stuck in pending, maybe few hours or so, whatever the interval that we want to do, so that even this the ones that we are stuck, we'll try to make sure that we update it. So that's the overall the pattern. Basically idea is to try to detach the server completely from the client and the blob storage, and let them take care of the things. And for syncing to our application server with the blob storage, try to rely on this event notifications and reconciliation. That's all. That's the whole idea of this handling large blobs pattern, and nothing much in here. And now this try to get this with jargon, so nothing much to learn here. Basically we have major cloud providers, AWS, GCP, and Azure. Their terms are different, but features are something. Upload URLs, it's called pre-signed URLs in AWS, and signed URLs in GCP, and SaaS tokens in Azure. Multi-part, we call multi-part upload in AWS, resumable and blobs in Azure. Events, S3 events, and here we have this pops up separately in the GCP, and here it is event grid in Azure. So CDN side, it is like this CloudFront is what is known in AWS, and Cloud CDN, and Azure CDN in GCP and Azure. Cleanup basically will have the lifecycle rules that, like I just mentioned, those chunks we can configure some lifecycle rules and get rid of them, so that we can save some of the costs that will incur if you try to store in our blob storage. And it's called lifecycle management in GCP, and lifecycle policies in Azure. So that's some terminology, just to better to get used to it. And now identifying like basically when to use and when not to is very important. So that's when only we'll know like this pattern will be applied in these scenarios. So simple rule, like I said, like if the files are greater than 10 MB, then straight away this the pattern that we just discussed is something that should trigger our mind, and we should try to just talk about it and implement this. So yeah, so basically greater than 10 MB, completely move from our server and use this pre-signed URL that basically we get out of the box from the cloud providers. And that's the thing, that is the only situation when we need to straight away think of to using it. And common scenarios like systems that we normally use on day-to-day basis, that like video related platforms, let's take YouTube, Netflix, or whatever it is. So everything we always like big files, 10 GB, 20 GB and all uploads, we need to handle through pre-signed S3 multi-part that we mentioned. And then once it is completed, let's say 100% is completed, now we know that S3 will have this event notifications and all those things. And using that, the other worker process, let's say transcoding or transcripting, and then other whatever the heavy worker processes that we can want to trigger, event notification will be a triggering point for those workers to start once the video is completed. So that's how like the one of the real use cases in applications that we use on day-to-day basis. Photos as well, let's say Insta or whatever it is, we try to upload like 50 MB plus photos and all. This also like we try to bypass the API and try to adapt this pattern. Again, event notifications, maybe we need to create some thumbnails or apply filters or whatever the sound, music, or whatever they have attached, and all those things we rely on this event notifications for those workers to process further. And file sync, the Google Drive, Dropbox, and all those things. Chunks will try to upload to blob, and this again multi-part upload pattern, we try to maintain that. And also this files share this generate time limited signed URLs that work without the recipient really having that Dropbox account. So even if you wanted to share the URL to the person who doesn't have that really account, the signed URLs will help them to access that. So this way like this pattern really helps to adapt to those scenarios as well. And chart also intake like WhatsApp and the other things that we use, media uploading and all falls back to the same pattern that we just discussed. So that's the thing. And again, we should also know when not to use. This is simple, small files less than 10 MB, don't even think about this pattern. That's the thing. And also synchronous validation is something is mandatory, and it's something is needed. Then just stick to this simple pattern, and don't even think about detaching the server from this picture completely. And also we have a need for compliance and data needs, like we need to scan before storage or so, like try to handle this for compliance reasons and all. This pattern again doesn't work. And this when the experience or tries to demand immediate response, like users expect instant feedback based on like file contents, like let's say like photo profile photo appearing immediately with like face detection or so. This async nature of like from the client to blob storage really doesn't work here. So we need to be synchronous and try to not to use this pattern. That's the thing. And just the common situations, what happens when we upload fails at 99%, and we know that chunk uploads resume from the failed part, and that is where, like, we need to rely on this multi-part upload and understand that pattern. And it's not like, we'll do all the way from the scratch. So that's the thing. This query uploaded parts, it has like AWS has list parts, session status, and committed blocks in Azure and GCP respectively. They resume from the failed ones instead of starting all the way from one. They track this session ID, this upload ID, and resumable URL. Like, basically they try to store in the local storage to survive when the restarts, like let's say mobile, where it has like least network connectivity. So in that situations as well, this really helps to continue even if they have like low data or low network and all. So this basically this if it fails in between, and if you don't know this pattern, the incomplete parts that are stored in blob storage cost us money. So that's something also we need to take care of it. And we need to definitely configure this lifecycle policy to clean them up, or maybe after every one day or 2 days or so. That's the like how do we handle those things. And like trying to prevent abuse, like a user trying to upload 100 MB file for just 1 MB restricted blob URL, present URL. So that in that situations will not let the user to directly upload to our blob. We try to introduce a quarantine bucket. So basically as a temporary file bucket, and there we'll try to look for scanning viruses, file type, and then basically an additional layer before our actual public bucket that we try to expose, because they might upload some malicious content and all, like the thing that is not usually encouraged to be viewable by all audiences. So those are the things, like we can try to handle this kind in these situations, and prevent abusing our storage, whoever is trying to use our generous offering and all. So that's what we need to first level is always try to cap file size in the preassigned URL conditions itself, like 10 MBs and all for every chunk. And then this introduce this quarantine bucket, and that's the only way to prevent abuse and all. And now the handling metadata, this we have already discussed. We always try to create a DB record at pre-signed URL generation time itself, so that we'll have an entry and the storage key and all. And after that only we give that URL to the client, and then client uploads through that URL to the blob storage. And once it's done through event notifications, we will receive an event, along with that the storage key. We'll look for the row using that storage key and update the status to completed. So that's how the pattern we try to always maintain this way, and that is what this is all about. So these are basically the kind of scenarios that we try to always look for, and see how can we improve, and also how do we ensure faster downloads. You saw the simple direct download. Try to introduce a CDN at the edge cache locations nearer to the user, so the turnaround time for them to look from the actual region where the blob storage is available will be reduced. And this CDN introducing for geography, and also this range requests for resumability. For example, first request, what, let's say I'm trying to get the file. I'll directly get from the blob storage. Let's say if it takes 200 milliseconds, and I know this is frequently accessed, then now I'll try to cache at the CDN edge, and next time whenever user tries to access that, we get the cached copy, it'll be just the 5 milliseconds. So you see the difference between 200 and 5 milliseconds. And then we have this range request. So this, whenever we try to download, this is quite opposite of the multi-part, and whenever we try to download, whichever is missed, only that bytes it tries to download, and making it as a faster using the local storage that we have. And so these are just the rough ideas and the ways and the solutions to handle all these kind of situations, and thus how do we handle big files and large blobs, and how can we fit in these solutions or so in the systems that we'll be discussing. So this is a simple one, simple pattern, and just you need to understand when to use it and when not to use it, and how it works at a high level. That should be it. Let's catch up in the next one. Now let's start discussing our patterns that we identified after having gone through every case studies of designing X, designing all those the Twitter, WhatsApp, and all the things that we saw. So now from those all that observations, there are a few key patterns. It's what for us to try to discuss on it, so that it can be helpful for us in whenever we are trying to design new systems of similar things. So let's talk about the first of that kind of pattern, which is the scaling grids. So here what is this pattern is basically here whenever our system grows very becomes very popular, then the read request might grow from hundreds to thousands or millions of users read request. So here the pattern is basically the read traffic, whatever we have, it grows way faster than whatever the write traffic that we have. So in that kind of situation, how do we handle such massive load, read loads that we are receiving without even crushing our primary database? So that's the pattern. So let's try to see what that pattern is about, and discuss. So the problem here, like I just specified, it's a read heavy traffic. So consider any application that we're using. So it can be YouTube, X, Reddit, or LinkedIn, or Insta, whatever it is. So all of this platforms you see obviously the feed. So whenever we open our respective app, definitely from our developers or system standpoint, we are hit with dozens of the videos, Twitter articles, or like Twitter posts, or any posts and Reddit articles, or so whatever it is. So each would require multiple database queries. So to fetch if it's a YouTube, it's a video metadata, and the channel information, user information, the likes counts, the subscribers counts, and the comments, and all those things. So that's just I'm just laying out such scenarios. So that's potentially something like it can be like hundreds of 100 plus read operations just to load particular feed on our platform. And meanwhile the write ratio, it might be just we post one photo or one video, or like occasionally, or whatever it is, write one Twitter post or whatever it is. So this basically it's very common in majority of the platforms. So for every video created, for every tweet posted and everything, the scale ratio, read scale ratio is obviously is 10 times higher, 100 times higher than whatever the write ratio is. So thousands of users read it, and even like consider any product, any application. So any e-commerce website, whenever every product is uploaded, hundreds of people, thousands of people in big magnet or browser, same applies to YouTube and everything. So that's the problem. So the read traffic is more than the write traffic to our server. So in the ratio, it will be in the ratio of mostly 10:1, 100:1. So how do we deal with this kind of situation? So make sure that the servers, whatever we have, they don't crash and they don't go down. How do we handle all of these situations is what this pattern is all about. So what are the solutions then? So this is the problem that we identified. So let's try to see what are the ways that we can think of whenever we are put under this kind of situation. So scaling rates, so we can solve it with the three approaches. So let's try to see what are those approaches at a high level, and then we'll try to break down into each approach and try to elaborate more on that. So first is basically for try to focus on optimizing in our DB. So it can be indexing, denormalization, vertical scaling. So we'll talk about what are they in detail as I elaborate of each approach. The other option that we can think of is basically scaling out. So here introducing read replicas and trying to shard our databases and all that stuff. The third thing is basically adding the cache layer between our database and server. So it can be application cache or CDN or edge locations, and so those are the like three approaches or the solutions that we can think of. So let's now try to discuss this first point, optimizing within our database. So first thing is indexing, like I just mentioned. So basically what is indexing? So let's just try to take simple analogy. So assume like it's a simple sorted lookup table. What it does, that really helps us to point to rows in our actual database. So like normally we read books, right? So like let's say I wanted to find specific chapter or specific section, we mostly try to look in the index section. So instead of scanning every page to find that exactly whatever we are looking for, so we check that index, and then it helps us to navigate to correct page or so for that section whatever we're looking for. So same applies to our database. So whenever we try to query, assuming we don't have an index, so this database what it does, it tries to read every row, meaning it tries to do every full scan of all the rows that we have in that table to find whatever we are looking for. But assume like we have an index, so what it does now, it can jump directly to relevant rows, like this what it does, the order of n, the linear scan what we are doing, it can change that into log of n operation. So that is basically, instead of let's say we have millions of rows, so like instead of scanning 1 million rows, we just now check in the 20 index entries or something like that. So this is how it's going to look like. So basically we try to assume like this is the memory. So here we first try to get the index. So this is the disk. So assume that we are trying to get the index. Once we get that index, we try to look up the right page from that index. So let's say we try to look for that specific page. It might be page 7 or page 6, just a random representation so that it is easier for us to understand. So this is something that we can focus on to improve the read operations or performance. So even in this indexes we have different types of indexes, like mostly we use B-tree for general queries, and there are hash indexes as well. They're mostly used for exact matches, and we have specialized indexes for full text search or geographic queries and all. So that is something again a discussion on its own, but that's a rough idea of what it is. So that is what. So first thing that should come to our mind whenever we are receiving higher traffic, first check is do we have an index on the frequently accessed columns or so, and all those things. So that's why so basically better to index on the column which is being frequently accessed by users. Then that really improves the lookup time and all those things. So that's the first approach. And now the second thing is we can think of is as a quick workaround is hardware upgrades. So sometimes what we try to do is basically we try to increase, let's say our the hard drive is having 4 GB RAM and 50 GB disk. So adding more RAM means that now our data can sit in memory more instead on disk, and faster CPUs and more cores meaning that it can now return query very faster to to the users whoever is trying to ask. So that way is something that we can think of, before we really try to figure out the optimal ways in an approach or so this can be a quick way as an hard fix or so to handle heavy read traffic till we figure out actual way to make it more performant or so this is one thing. So we can just right away upgrade our hardware, maybe adding more RAMs and more disk size and all those, more CPU cores and all those things. So that's the another approach that we can think of as a way to handle this the scaling reads thing. Then the third the approach in first one is basically denormalization. So here we know what is normalization is. Basically that's like we try to structure data in separate tables or so to reduce redundancy and and to avoid storing duplicate data. That definitely helps. So because that really helps in saving some space that we need in a storage, and also it saves storage, but the other way around, it makes queries more complex, meaning now we need to do multiple joins to bring data back together from across the tables and all. So that's one thing. That's the normalization ideally. So that is the case when we have like balanced read and write traffic. And for read heavy system, it's okay to go with denormalization. So basically the quite opposite of normalization, where it's okay that we store redundant data because here we're doing trade-off of like storage for the speed of retrieval. So now what we do, instead of doing multiple joins to get, like, let's say the examples here, we have customers table, orders table and products table, and let's say we wanted to get the users related info. This is how normally we do, if it's we have followed clean normalization and all. So we try to query the customers table and join orders and also join products, and let's say we have other order items and other tables that we have. We'll try to do multiple joins on these tables and get the all the information that we need related to that specific order or user profile or whatever it is. But let's say if I denormalize and I try to decide to create one table called order summary, so to get the order profile for a particular user. So this can be something like this. I'll try to have this table with directly I store username, the location and the date and the product and the cost of that. So now whenever I would like to get the details for viewing the orders and all, I can directly query using this columns that we have: customer name, order date, product name, price, from this table. And so there are no multiple joins or so, and it makes read more efficient. Of course the trade-offs is like whenever we do some updates and also the write operations, now we need to make sure that we need to do this at multiple places in this table and other tables that we have and all. Again, that's a trade-off whenever this read traffic is very high when it compares to write traffic. So that's one thing. So and also, like this is the one way of denormalizing to handle this read traffic. Then mostly let's say people are looking for analytics related queries and they wanted to see, and for that kind of situation, so basically where we need a pre-computed expensive aggregations and all, people try to create materialized views. So let's say, for example, let's take an example of an Amazon itself, like e-commerce products. So whenever we wanted to calculate the review of particular product, like it will be basically average of that product ratings across all the users whoever has given, right? So instead of trying to calculate that average on every page load, we can compute them once, like via some background job or so, and store the results. So this way now like and expose that as a materialized view, and whenever we wanted to now get the product ratings, so we can just use that materialized view as, like, let's say product underscore ratings to get that, and use that to showcase in the product page, instead of trying to read and doing this calculation of rating across all things like with average or so, and showcasing instead of that. So this way, like we try to reduce the load on our DB if it's a read heavy traffic. That's the this thing that I was talking about, materialized view. So we try to pre-compute this expensive aggregations via background job, and this basically we try to store in this way, and we just now do this lookup using this thing. So yeah, this will be a scenario just to avoid that. Yeah, that's like the first approach, or the first things that we can immediately think of. Now let's go to the second the approach that we have listed down. First thing is trying to introduce read replicas. So what do we do here is basically we now try to scale behind a single database, is adding more ways to copy data from our primary database to additional servers. So the idea here is basically whatever the writes happens to in our application, they primarily go to this the primary database, whatever we call leader or so, and then this reads will be slowly propagated to all the followers that we have to the other databases. So now whenever user tries to request for some data or so, now we will not divert that traffic to this primary database. This handles only the writes. The reads will be stored from all these followers. So this way we are trying to delegate the traffic to multiple databases, which is the read replicas. So, and also like even this not just in handling this fan out of like reading traffic delegation, but also here it handles in case of redundancy, meaning let's say this leader failed. So that way whenever it failed as well, for write operations, this can be any of these followers can be promoted as a leader, and the writes will still be handled and will not lose any data. So all the read and write operations will be going smoothly as usual. So that's the thing. So that's how we try to handle. And also here we have like asynchronous updates and synchronous updates. So here basically asynchronous in the sense what do we do, writes will happen but still followers will have the stale data. That's fine. Eventually we'll try to be consistent, so maybe in the batches or some background job we'll try to copy this into data. That way though the read replicas might serve some amount of time stale data, but eventually end users will see updated data. If it is a synchronous, so what happens in that case, we first write it to leader, as well as along with that we need to write all that to the its followers as well. Only then we acknowledge to the client. So this way now all remains consistent, but the only thing is it adds latency to the users or whoever is experiencing and all. So they're also like what are the situations where synchronous consistency is needed, asynchronous consistency is needed, and that way we need to decide which one to choose. That's the read replicas approaches. And the other approach is basically sharding. So here we know that above read replicas that we just discussed, they distribute load, but actually in reality they don't really reduce the data set sizes that we have. Basically it will be exact copy of whatever we had in a primary database and all that stuff. And now assume like our database grew so large that even all the steps that we followed above, like indexing, denomination and all, still doesn't help. That's where like now we need to think about how can we split into like based on some functional or so that's again trying to divide into smaller pieces, so that particular group of users will be served from that specific shards. So here let's talk about first one, functional sharding. So here basically what we do, we try to split the database by domain of feature. So here let's say like the server, all orders related thing, I'll try to put the data in that DB, and all the data related to customers I'll try to keep it in the customers DB, and for reviews in this way. So basically the idea is basically here is to shard or split by domain or feature, so that now each request related to that specific feature or domain, it's that specific DB, rather than all keeping this in a single database. So that's how like we try to shard it by feature also. So that's functional thing. And the other thing is basically trying to shard it by geography. So here is basically, let's say our application is popular and it has a global appeal, and we have like global users presence. So what we try to do now, the DB related data, so whatever the data that we have for specific user, let's say user is from US or UK or whatever it is, so we'll try to store in that specific region itself. US related data will be stored in something like US region availability zone and that specific region, and same way Europe related users will have the data stored in that specific region DB, so that now each region's data lives very close to its user, and whenever it's trying to retrieve, the latency and the turnaround time will be way faster than trying to store in some different region. So that way we try to shard in this way, so that the specific regions users goes to that DB only and not to other DBs. So this way, like functional and geographic sharding, we can try to think of even whenever the approaches that we discussed before, like indexing and the other things, read replicas and all. This is the other approach that we can rely on. So fine, so that was the second thing. And now let's talk about the third one, the adding the caching related layers. So here we have assumed like we have optimized using approach 1, approach 2 and all those things, but still we need more performance also. That is where we have to think about this caching and all. So basically what caches really helps us with is basically they provide a better performance for very read heavy workloads. Because most of the platforms that we see that we use as well, they experience very high skewed access patterns. Let's say like most viral videos are watched by most users. Same thing on Twitter, viral tweets is read by millions of people. So you understand the point here is like, right? So it has like very high skewed patterns. So even like even in any of the like e-commerce other platforms, popular products are viewed by thousands of like millions of people. So what does this really conveys? Basically we are querying our database for very similar data, like identical data. So basically the data that is rarely changing between requests. So that is where like the data that is rarely changing between requests from multiple users, that's where like we need to think about the caches introduction. So that's the that's where it helps really. So just trying to store frequently accessed data in memory, and whenever we have that, we try to read it from memory instead of from the disk that we have in our DB. So that's the thing. So let's talk about now the application level cache. So this is standard pattern wherever we see. So basically here we have the server. So what we do, we will have some Redis or memcache or whatever it is between our application and the database. So first we try to check in the cache if it is there. If not, only if it's missed, only then we'll try to read that and then populate the cache. So the next time again, whenever we first check the cache, we try to retrieve from that. So this is the application level cache. So this works fine most of the cases. And here again the caches, we have like multiple invalidation strategies. So here what do we what are the approaches that we normally follow? Like make sure that caches always have the
up-to-date data, and they don't really serve stale data and all. So what are the ways that we can follow, like eviction policies and all? So first thing is basically time-based expirations, so TTLs. So what do we do in this case? Mostly we'll try to have this TTL of 5 minutes or so, and post that will be removed from the cache, so that now we ensure that at least we don't serve the stale data. And the other approach is basically write through invalidation. So here what we do, we try to update or delete whatever it is from our cache immediately after writing it to the database. So this way it ensures consistency, but adds a little bit of latency for write operations and all. Again, that's a trade-off. So, and the other is basically write behind. So it's simple. We'll have some asynchronously some queue or whatever background job. It tries to sync between database and the cache, and try to make sure that cache is having up-to-date data. So it's asynchronous again, but it's quick. Because we are not waiting for the cache writes, right? And the other approach is basically tagged invalidation. So we'll try to keep the keys grouped by tag. Let's say like user 1 to 3 videos or so we'll try to invalidate all these entries with that specific tag when that related data changes. So that way it's really helpful for very very complex dependency, but it again requires us to maintain this tag relationship and all, but that's one way. And the other is basically versioned keys. So we'll try to include version number in cache keys. So every time any updates or anything that changes, we'll try to increment that version, and so naturally the older versions will be invalidated, and again here we need version tracking and all that stuff. So mostly in real systems we try to use combination of like TTLs and try to follow some other approaches that I just mentioned, right through, right behind. So combination of one or two mostly, and then try to meet the requirements of whatever the system that we are currently designing. So that's the thing. And it's important thing is like how do you decide even the TDL for specific application. So that's also one of the point that you need to lay a bit of attention on. Let's say like let's say like in Twitter or something, let's say I'm updating my photo or some username or so, and if the requirement that we have, it's okay if user can see stale data for 5 minutes, and then we know that 5 minutes of TTL or something like that. So that's how based on the requirements and proper understanding of the system that we are building, TTL has to be decided upon. That's all the invalidation strategies for caches and all, and that was like our application layer. So now let's discuss about on the CDN and edge caching section. So here what we do, these CDNs they try to help us to cache this shared content at global edges. So what do they do now is basically users can read from the nearest edge location instead of reading it from the region that we have stored. So this way anything loading of images or videos or something like that, this let's say user from US can use this edge location to read that specific content, and instead of getting it from the original region or whatever we have. So that way introducing CDNs and edge cachings is basically helps us to reduce this read latency issues, and also distributes the read traffic to this global edge networks that we have normally provided by cloud providers. Fine. So those are like, three approaches that we can think of, and that's how, we try to deal with this pattern. So now the thing is basically when to use what and which approach to follow and all those things. So first of all, we need to identify in our design or system that we're trying to deal with, try to identify the one which is having high volume. Like, let's say we are building an API, so let's try to see which endpoints are receiving high volume reads, and try to first focus on optimizing that one. So that is the thing. So basically we need to first identify a spot, the very read heavy endpoint, and then we need to estimate how many reads are happening per second or so, like what's our capacity, and then we need to think about all the optimization steps that we just discussed. So first try to prioritize indexing within the database, and trying to add caches in between application and our DB or CDNs or whatever, and then think about adding read replicas and sharding and all those things. So here basically this order really matters. So try to focus within database, do not try to complicate it. So query optimization first is our preference, and then caching, and then only replicas and sharding, because the simpler the better first, and then try to complicate things. So that's the thing. And now common scenarios in our discussions whatever we had. So URL shortener, so that was like extreme read write. I think if you hadn't had a look at that discussion, you can just go and look at it. So that's like scenario where it is read heavy thing. And same way here, book my show, district, or whatever event related booking platforms. So people try to see which seats are vacant, or like is it open, or like how many are booked and all. That's also very read heavy kind of systems. Same thing, news feed, we are trying to read any news feed or Twitter feed or any post feeds, what are all the social media platforms that we use. And video platforms, reading posts and watching videos and all those things. So these are all the situations mostly have this pattern of like read heavy traffic and all. So these are like few examples that we can really connect this pattern to, and that's the scenarios. These are the scenarios that we really need to think of, the approaches that we discussed above. And finally that was like when to use, and now when not to use also it's very important to understand. So basically don't try to think about these patterns approaches whenever it is read light and write heavy. So here let's say Uber related, so it has like location updating. So write is very write heavy because every 5 seconds or so we need to update our locations of our drivers, and so that there we need to focus on how can we scale these writes, not the read. So and also like the whenever the consistency is very important in case of like payments, inventory and all. So there it's something we should not focus on read, but instead focus on writes. So and all those things. And and small scale, let's say 1k users, we have a single db trying to tune that, that should be fine. And even this real-time collaboration related scenarios are so scaling reads pattern is something it's not feasible. So these are the scenarios, like small scale applications like write heavy location updates, and strongly consistent systems like payments related or inventory, or collaborative systems like Google Docs, and anywhere real time is involved. So don't even think of this scaling reads pattern, and this is not suitable for that. So that's the thing. Basically not to use in those kind of situations. So here let's try to take couple of the scenarios. So let's say like we are seeing that queries are slowing down as dataset grows. So what is the immediate thing that we need to think of is basically we try to first add an index. So without an index, what we do for every lookup, we do full table scan. That is why queries are slow. So whenever we try to add an index and a column, so we are querying very frequently. So let's say I'm querying on this or customer ID. So after index scan, so I do instead of doing let's say on million rows, I do some lookups on 20 rows or so. So that way we try to first add an index on a column that is frequently accessed, and try to speed up this queries return time. And if you're trying to rely on multiple columns, we can add an index on the columns in the same order that we are trying to retrieve from. So that way it really helps us to make the queries faster. So fine. So the other scenario is, let's say we have millions of concurrent reads for the same cache data and all. So let's say a popular personality posts something on our platform, and now suddenly all of his followers are trying to read it simultaneously. So ideally one cache can do what, let's say 50k requests per second, and so now they're getting 500 grand or 1 million requests per second for that single key. So now this cache starts timing out and requests fail, and our site goes down and completely. So this is basically the hard key problem. So first fix is basically we'll try to coalesce the request, meaning try to batch the request whatever we are trying to get. Instead of making one request for every query that we are receiving, batch it for let's say calls. Let's say we have 20, we are trying to batch it, and we make one request for this 20 queries whatever we are receiving. So this way we will try to avoid hitting the cache for every same request that we are receiving. And so yeah, that's the pattern. We'll try to combine multiple requests and all into single request, and this way we reduce this. Even when that is not enough, now we need to distribute this hard key whatever we are talking about. So that is called hard key fan out. So here what we do, we'll try to store the key itself as n copies. So now clients can pick one at random, and now we are trying to spread load across the cache servers. So here this is what I mean. So this key we'll try to split it with the additional the key we are trying to add, like this hard key 2, hard key 3 and all. So now the client can pick from any of these keys that we have, so that every key now is serving same data. So that's how we are trying to distribute even the hard key into multiple keys to the clients. So that's one approach to avoid this hard key problem whatever we have discussed. Then the other scenario is basically how do we handle this cache stampede. So here the situation is basically whenever the hard keys, whatever the TTL that we have is expired, and now we are serving everything from that cache, right? So all of a sudden now they will try to hit our DB instead of, because cache is a miss. So now every request is missing all at once, and it tries to slam this DB. So that is where now again the other approach is basically probability early refresh. So here what we do, every read request that we have, let's say assume that we have TTL as 60 minutes. So every read that we receive, will try to increase the chance to refresh early. Let's say we have 50 requests or so, so we'll try to refresh 1%, and same 55 requests 5%, and like that we'll try to make sure that based on the request count that we are receiving, we'll try to refresh this way probabilistically. So here again all, let's say 100k requests are missing at minute 60. So that is like last thing, and DB gives up. And the alternatives again here is basically having some background refresh job, so that we do it in well in advance, like maybe 10 let's say 50 at 50th second itself we try to do this refreshing and all those things. That way we can try to avoid this stampede related things, trying or everyone is trying to make a request at the exact expired time and all. That's one situation. And the now how do we handle this invalidation? So when data updates need to be like immediately visible, so like even they can't tolerate like some stale data even for a short span of time. So that's where like cache versioning we need to think of, like I mentioned. So basically we'll try to maintain multiple versions for the same thing, where with every update the version increments and the lower ones will get invalidated, and the information will be stored from the latest version, such that the immediate updates, even the cache invalidation, will always showcase the latest information up to date in a immediate way. So that's the one thing. So we'll try to bump the version in the DB as well, and then we try to route to the new key, and that way like so only thing is basically we need to worry about maintaining version state in our DB, and then check for proper updating and syncing between cache and DB. So that's thing. So on write, what we do, we try to bump version in the cache as well as DB, assuming like we are doing in transaction also. And now this let's say new key, old key was like order 789 v56, so now it becomes v57, and same thing we'll try to store in our DB as well, something like this version 57 and so this way again we'll try to keep it and make this as immediately visible to the end users. So these are the ways or the things that we can think of to handle this scaling reads pattern. So to conclude, this is what the clean progression or the picture that should be in our mind. Try to first try to do optimization within our DB, like indexing, denormalization and all that stuff. And first, so even if that doesn't serve, then try to scale out horizontally, adding read replicas or so. And even if that didn't serve after read replicas are sharding, then introduce this caching at application layer, and also the CDNs are so on invalidation, like I just said. Try to follow any of these things and handle all the scenarios of hard keying and cache stampeding and immediate visibility and all those things. So these things is what really matters, and the adoption, the linear progression, this is how it should be. So first, like always, the principle should be trying to start simple and then prefer all the approaches that we described. So this is all about scaling reads pattern, and the next one will be scaling writes. So let's jump on to that. Right, now let's discuss about the second pattern, which is scaling writes. So it's just the quite opposite of what we have discussed in scaling reads. So here basically it tries to address the challenge of like high volume write operations, when our single server or single database truly becomes a bottleneck in overall of our design. So if our application grows from like hundreds of writes to like a few thousands of writes to millions of writes per second, then this individual servers or databases that we have, it will hit hard limits on this disk input output, CPUs and network bandwidth and all that stuff. So that is where like if that situation is kind of something that we are thrown into, so what are the solutions or the approaches that we can think of, and how can we adopt them as if we try to implement specific design. So that's the pattern. So let's try to see if we can how it evolves and all. So here the scaling writes, the problem is like I just
mentioned. So during high writes per second, so assume like this is a graph of the write throughput versus the time. So as with time, if more writes are hitting our server, that's when actually it will be the bottleneck for our server or a database. So these are the situations, how do we deal with. So let's see the approaches that we can come up with. So the solutions, so to handle this kind of situation, there are a few approaches, and then we'll try to elaborate one at a time as we keep diving deeper into each of the approaches. But let's try to have a quick look at what are each approach is. So first one is vertical plus database choices. So here trying to like bigger hardware, so I'll talk about more on that. So and then the right optimized database, trying to choose the right ones, the database that is specifically built for kind of system that we are building. So that's one thing to look for immediately. Then the other way is basically trying to shard and partition. If you remember, we had a brief discussion of sharding in scaling rates. That was just one of option in scaling rates, but ideally that's not adopted in like to solve the problem of reads. Mostly it's adopted to solve this writes traffic. So here this is where sharding is also one of the options. That also it has horizontal sharding and then vertical partitioning and all. So that is the second option. The other is basically we have an option of queuing plus shedding. So here we'll try to to handle the spike of a traffic, we'll try to introduce a queue in between our server and application, so that handles a spike of traffic, and it each will be picked up by our workers or whatever it is. So that's one way. And shedding is basically trying to see if we can reduce the unwanted request, and only basically let's say we have a server which is keeping track of the likes or counts for our videos or posts or whatever it is. So it's not necessary that we need to like 100 people is liking it, so every time we need to increment it. Maybe just try to keep the likes in order of like a power of 2 or power of 10. So only when that is it's meeting that, we'll try to increment it accordingly, so that we don't lose the actual value too, and also we are trying to drop all writes at once. So like just that was just one vague example, but we'll try to elaborate on that. So that's the rough intuition of this queue and shed. The fourth is basically batching plus aggregation, and this I think it should be, we'll try to batch writes mostly in kind of like when we are looking for aggregate related queries and all analytical related queries. And hierarchical reducers is basically it's kind of like complex approach, kind of a very edge case, which we'll talk about in case of like the live commenting related use case. We'll discuss about that. So now let's try to elaborate on this first one. So vertical scaling and write optimization. So this one is basically first one to just blindly go and try to increase the hardware that we have currently for our specific server or database. So because we know at least we know the basic understanding that writes are bound by a disk input output, CPUs, capacities, and network. So let's say like we have our single server with DB 8 cores and 1 GB network interface card, and it roughly this capacity handles 1k writes per second, assuming that we scale up so to 200 cores, and so it handles like 50k plus writes per second. So that's like immediate way whenever we see this this sudden pattern, the first measure that we can take, so that it'll help us buy time to actually think logic wise or algorithm wise or something in the code or something that we can really make it efficient or so. So that's the one thing, straight away simple way, just trying to upgrade our hardware. So here basically the only thing is we just need to be very careful with appropriate numbers that we do, like what is the writes or second, like ops, like math calculations per second, and so that understand the hardware which can support that numbers, and accordingly scale up things, because mostly really often helps us than we normally think. We might think this is a vague solution and all, but really it helps it to buy us some time. So that's like the vertical scaling, straightforward. And now this database choices. So here this is very important. So basically here we need to be very careful of what kind of system that we are designing, and try to choose the database that was built for that. So first we need to think in that direction. So is it write heavy on so then we need to think of, like, what are the databases that was meant to handle that kind of scenario. So for example, here let's take an example of a Postgres versus the Cassandra. So assume, like, we have lot of writes coming in to our system. So instead of preferring Postgres, it's always good to go for Cassandra, because some of the traits of the Cassandra is basically it's only append only log. So whatever the writes that it will be receiving, it will be appending. It's not like in place update like Postgres does. So this traditional B tree, what it does, like, assume, like, these are the some data that we have in our Postgres, and whenever I wanted to write, so first, it tries to find some specific thing that we wanted to write or update or so it does basically in place update, and so looking for that specific thing and trying to update it. It's basically the turnaround time for is basically high, and as writes requests are more, so the traffic that we are receiving at scale is something this DB cannot handle. So that's the situation, like, this append only log, we don't do any operations and all, so it will be quickly able to handle, assume like roughly it can handle 10k plus writes per second, whereas, like, this is like 10 times less than what Cassandra can handle, which is 1k writes per second. So this is the only downside is basically this reads become slower, because that's a trade-off, because we know that write traffics are more, and this reads is something that we need to we can deal with that. So and this reads would be fast. So that is this first consideration, writes for just read, and so basically, like I said, optimizing writes usually cost this read speed and all, that's fine. And so that was one example of, like, the choosing the right databases. Should we go with the Postgres, B tree, traditional, and then the Cassandra, append only log, and like that. So like that we have specific write optimized stores. Like if it comes to time series related stuff, we have like in InfluxDB or timescale DB, and log structure databases like the level DB, and column stores like we have ClickHouse, which can handle batch writes efficiently for analytics workload. So if you know this various options that we have for specific scenarios and all, if we have rough idea of all of that, it will be easier for us to make a choice. So that's the the point is all about understanding the databases, and so that we can make a right choice for our specific application. So that's how we can handle writes properly. Now let's go to this second point, which is sharding and partitioning. So here basically assume, like, we have tried with our hardware upgrade and the database choice and all. Now basically assume, like, we have chosen Cassandra and some hardware which can handle 10,000 writes per second. So this we can basically handles one server can handle that many writes per second. Assume like we are receiving more requests, more than that 10k plus and all. So that single server is something that cannot handle. So obvious thing is basically try to split it. So meaning had more servers of that kind. So that's where, like, the sharding is basically. So let's take an example of simple things that we normally use mostly in any of the application, which is Redis. So Redis cluster. So basically here what we do, so I'm just taking an example of Redis cluster here. So each entry in our Redis is stored with a single string key. So the key that we have, so these keys are basically hashed using some CRC function or whatever it is to basically determine the slot number. So slot number, this basically what do they help is helping us to maintain the mapping two servers. So this let's say I provide a key as a build, and using that hash function I get some 1 or 2. So I know now the slot 1 is mapped to server C. So this basically whenever now clients request this thing, so it will find this slot number and it knows which server to write to or so. So just simple example, now whenever I wanted to write a value to this, it hashes the key to determine the slot number and looks up the server responsible for that slot, and it will send this write request to or write accordingly to that server. So this basically what by doing this, what are we really taking help is basically we have spread our data across this servers, like server A, server B, and the server C. So that way, now each server can handle on its own, and we are not hitting the same server and trying to handle. And now the here basically the one thing we need to carefully decide is how do we choose a good partitioning key. So that is the thing that we should focus on whenever we try to think of sharding. So basically here how do we choose, and if by chance assume like we have chosen the wrong key, it's again taking back us to the same problem that we have, which is not able to handle the scales of writes that we are receiving. So that is what so let's just say that the good key, for example, user ID is a good key. Let's say instead of user ID I decided to use the country as the partitioning key. So now the situation is I think straightforward. So now what happens is basically we'll try to end up with a lot of writes going to this populated countries like India, China, and so, and very few writes going to this very sparse countries like Highland and all also. So this is again trying it's bombarding few servers and again becoming the bottleneck and throwing us back to the same problem that we have. So what if we choose the good key, which is hashing user ID? So hashing user ID, it gives like 100 to 200 one server can handle, and other 300 to 400 number, let's say, that other server can handle. So this way it gets evenly distributed, and it tries to handle the traffic cleanly. So this is very important to understand what is the ideal key that can really help us with this partitioning and all. Fine. So now that was the horizontal sharding, so basically trying to split rows. Now let's discuss about vertical partitioning. So here the vertical partitioning, what it does, it tries to split columns instead of rows. So what ideally we do is we separate different types of data based on their access patterns and the scaling requirements for them. So instead of keeping all those columns in single table, we try to break it apart and how it is used. For example, so so one table, let's say we have this videos table, ID, title, description, upload date, view count, like count, and watch counts. So this is let's say if it's getting hammered from all sides. Vertical partitioning, what really helps us is basically we'll try to split into multiple tables, these columns, and by patterns. So first we can break it down to video meta, so where it'll have ID, title, description, and upload date. So this basically, if we try to divide this by access pattern like this, same like video stats, I might break it into view count and like count, and video events like watch events and timestamps and all. So this way we try to split into specialized tables, and once we have now logically separated our data, This gives us a lot of leverage even to choose different databases which really suits for that specific case. So for example, here metadata mostly it is write once and read many, so we can choose for standard or b-tree related stuff like Postgres and all that should be able to handle. And here video stats, view count and like count. So if we know that it is something like the write frequency is very high, so in that case we can choose some in-memory counters or in-memory database that really helps us with directly writing it memory instead of going to disk and seek in and seek out there. So same for video events. Since like it's a like kind of like watch events and timestamp, it's like append only that we wanted to choose. So this here again we'll have a choice to make the ones that it's optimized for, like time series related database and column or related database and all that stuff. So that way if we try to partition in this vertical way, we'll have the choices to choose our own database. At the same time, operational complexities also is something rises, but that's a trade-off that we are going to make. So this is like the horizontal sharding and vertical sharding. So now let's jump onto the third the approach that we have, trying to handle the burst with queues and load shedding. So here basically the idea is simple. This queues is first one, write queues. Queues basically we try to use to decouple the accepting writes to processing them. So then that queue really acts as a helper to absorb any sudden spikes that we normally see. So assume like, so it's always the same. So we try to introduce the queue between our app server and the database. So what happens is basically whatever the app is trying to make a request, we try to add an entry into queue with some data that needed for our worker to pick up, and this whole heavy work will be delegated to our worker servers, and that worker will pick it up and does the heavy lifting for us and tries to deal with the actual business logic or domain logic that we have. Once it's done, it'll try to update our database for that specific status, and then this application server can directly check for the completion of status from our database. So they are basically this is the thing. So mostly used to observe this short burst, but again here even in the case if queues become unbounded, meaning if writes outpace the db for very long, the queue becomes really unbounded. So a lot of things will be piling up in a queue. So that is where again to handle that we try to use this load shedding approach. So this load shedding approach is basically that's also one of the strategy to thing. So here like I mentioned, if we are overwhelmed with a lot of requests, now we need to think of like how can we drop any least useful writes to keep our system alive under even such heavy load situations, and also make sure at the same time we are not losing any data that is really valuable for us and for our users. So let's take an example here. So again these are all situation related and the system that we're trying to deal with. So let's take an example of like Uber or the other scenario. So let's take an example of Uber. So we know that driver or the user driver, let's take an example, driver, he tries to report a location, and so we know that we are receiving requests like every 5 seconds or so. So it's okay that if we lose like a few of the 5 seconds location updates to our database, until unless we have his latest location write to our database. So meaning, so for example less than 10 seconds since last update, we can just get rid of it. We don't have to like only during the high scenarios, high overload times, and greater than 10 seconds since last update, we can try to take that and update into our location db. So this way all the holder rights is something that we are trying to shed it and keep the latest one. That is what really matters for us. And this basically because ideally we need just last seconds of the previous update and not like more than that. So that's why, like, now we'll try to drop this, and this is one of the strategy to deal with that. So here basically because we know that anyhow the fresher right the latest location update is coming anyway with our real-time updates or whatever it is, so that we know it's coming. So we'll try to drop the before ones, and that's how we handle and keep the rest. So that's one of the strategy. That's like the example of what I mean for load shedding. So that's one of the example. So same way the other situations for analytic systems, we might drop the few of the impressions for a while to focus on more important metrics or more clicks and all like that. So it varies application to application, and that's where, like, we need to make some serious decisions based on that. So that was like the shedding. So now the fourth approach is basically batching and hierarchical aggregation. So here first let's talk about this at the application layer. So idea is simple. What is this? Basically we'll try to buffer many writes into one bulk write. So that's like let's say we are receiving 100 writes, so I'll just try to maintain it in my memory or so, and once I hit that number, I try to do that all 100 writes at once into our database. So that's like this is basically chosen when our app isn't basically the source of truth, mostly in kind of like situations of the analytics or so. So for example, let's say like we have some consumer or analytics consumer or other things as a consumer for our Kafka topic. So this like assume like it does some logic or business domain application or so, and it does some processing, and then it tries to the database. So it's consuming the stream, and it is doing something. So here what we do now is basically we'll try to batch up the writes before we send them to the database. So this way like I try to batch write 1, write 2, write 3 till n, and I do just one bulk write to the database. So even here if the application crashes, we can reread from this the Kafka topic, and this ensures that we haven't lost even any data. So and this is the thing. So basically now we have reduced 100 writes to one round trip, and okay, and before even flushing into the database, like I mentioned, you'll try to reread Kafka and again do the same thing. So that is the thing. And now the application layer is something that I discussed. Now intermediate processing is the another option as well. So here this is basically what it helps us is basically it's a middle service. Here it tries to helps us tallies events like over a window and then forwards that one update per key. So like to understand here, let's say we have like like batcher or so for our post or video or whatever it is on our platforms, and let's say like this we have the Kafka like events the topic or so. So let's say for one video he option A as like the clip 4, option B as like clip 5, or like some other guys like the same clip 4 and all. So now we are receiving events like this. So this like batcher, what it does is basically this tries to keep the like count for that specific clip or video. So we know that from now here this events clip 4 has 2 likes and clip 5 has 1 like. So here ideally we'll try to show the number of likes or comments also for specific post or video on platforms, mostly not like who has liked and all. Mostly again that will be another, like, once user is trying to view that specific video, then we might show all those details. But in a mostly in a feed and all, we'll just try to show count. So here the count is what really matters for us. So here this like batch can help us to keep this like count events. And once we have this for this clip, and so we are trying to do update to the counter for that video, instead of doing for every time a person is liking that clip or clip or so this way basically, like I said, over a time of window, let's say 1 minute or so, like that, in 1 minute whatever likes has been received for that clip, we do at once in that window. So let's say like we have 100 likes in that window, so then we do 1 write instead of 100 writes to that specific event. So basically again this only helps this events are coming in that window, or else again it falls back to same rights whatever we have. So but that is the this intermediate or the processing is something that we can introduce like this, trying to understand the window patterns and see if we can reduce the writes to database. The idea of any approach is basically trying to reduce number of writes to database. That's the thing, simple. So that's the batch and aggregations. And this, now that was at the intermediate processing, and we saw at the application layer. Now let's take a look at the database layer. So basically most databases basically they have configurable options, for how often the writes are flushed to disk. So as an example, let's take Redis default configuration for that is basically it will flushes writes to disk every 100 milliseconds. So that means, let's say if we have 1000 writes in single batch, we only write to disk 100 milliseconds after the last write. So the idea is basically we can configure that, and also at that layer as well, if we wanted to reduce number of writes to our store, and increase this based on this, so that even the writes are taken writes hammering our server is something that is taken care. So like last option at the even at the database layer is something that we can work on. Fine. So these are all examples of Redis has, and Postgres has write ahead log batching and all those things. So here again disk becomes the bottleneck. So that's the thing. Fine. So that was all about the batching and all that stuff. And now let's try to discuss this hierarchical aggregation. This is the last strategy. So in basically this is kind of complex things, and it's also extreme case. Like let's say high volume situations like the analytics and stream processing. If you see those kind of situations, we really don't need to store individual events, and instead basically what we need is aggregated values or views or whatever it is. So this, we know that if it is aggregated things, that can be easily built up incrementally. So that is where this hierarchical aggregation is something really helps us in processing data in stages and reducing volume at each of the stages in that process. So the example, let's take we have video streams and all that stuff. So in that situation, viewers they can comment and then like comments on that video stream or so. So whenever a specific viewer or so performs this either of these events, then all other viewers or whoever are viewing it should be notified of it. So you get the situation, right? So this basically creates very ugly situation for us if there are assume millions of viewers and millions of users are writing, and now all of the writes needs to be sent to all of their pages. That's where millions write, and every write must reach millions of pages. So this is the situation. So everyone is trying to do like events or like commenting and all those things, and this is our app, and then and this is something that again we need to broadcast it to all other viewers who are viewing. So this is the situation. So here first step is basically how do we deal with this kind of situation is we can try to simplify from both standpoints, and let's see like one step at a time. So first step is basically we can add broadcast nodes, which is a fan out. So here we know that all our viewers are basically looking for the same consistent view. So basically they wanted to see all the latest comments and counts associated with them, like likes or so and so. So here the idea is basically we will try to assign these viewers to a broadcast nodes instead of directly to our root processor. So this way now instead of now this root processor writing independently to each of this viewer, now we can just write out to this broadcast nodes, which that will help us forward the updates to that respective viewers. So that's the idea. So now basically what we have reduced is basically instead of writing it to let's say n viewers, we are only writing it to m broadcast nodes. But again we have we are taking care of the broadcasting thing, that's fine. Other side, now we have this problem, how do we deal the same way with the incoming events from all the viewers? So same thing we can try to handle in the similar way, this the fan in thing. So here what we do, this we'll try to again introduce some write process here. This what it does, it will try to aggregate writes over that window, what I said, like let's say 1 minute window or whatever it is, and we'll try to let that viewer connect to this specific write processor, and then that will be sent to the root processor, and then that will merge all of them and again broadcast it to the respective nodes. So here basically how do we choose which viewer goes to which write processor is basically can be chosen based on the like ID of the comment, or like for example likes, the comment ID it is liking or so. Like I'm just stating here, we are talking about an example of live video streaming for comments and all. So now if we choose based on that ID of the commit, so if that specific event is happening for that comment will be written to the specific processor, same like for other comment it might go to the other processor. So this way it will know which write processor to reach it, and then handle it over a window, and then send it to root processor, and then this will merge all of it and broadcast accordingly. So this by aggregating this data with this write processors, and again disaggregating with this broadcast nodes, we now have drastically substantially reduced the number of writes that we need to do for each specific user. I know this basically introduces some latency by adding steps in between root processor, but like that's the actually the the core of the hierarchical aggregation, and that it really helps and helps us with handling such scenarios. So these are like all the approaches that we can adopt to solve this scaling writes problem, and depending upon situation try to adapt the one which really helps us solve the problem. These are the ways that we can think of. Now again, like I said, when to use all of these approaches and all that we discussed. So it is always the question falls back to like try to identify which is very write heavy endpoint, and then do some back of the envelope estimations like writes per second versus capacity, and only if it's we see it's a scaling writes problem, then deep dive into one of the approaches that we have discussed above. So for example, with millions let's say posting, we will definitely hit write limits. and then you need to check what's the throughput, and if that is the case, then we need to deep dive into one of the approaches, any of the approaches that really makes sense for that specific system, whatever we had discussed about. That's like falls into this scaling rights pattern. And so basically, like common scenarios is something like this. Most social media platforms like Instagram or what social, so there they try to use sharding techniques, like sharding by user ID and vertical partitioning, profile, post, analytics, and news feed. This they try to they try to adapt this fan out and fan in approaches mostly for popular accounts or so. And for search, this write heavy pre-processing and partitioning plus batching and all, they try to adapt these techniques. Live comments, which I just specified, the hierarchical aggregations and all. So these are like scenarios and where one or two approaches from this pattern is something adopted and then built to tackle those rights scenarios. So fine. And when not to use, basically do not try to scale prematurely, just try to do back of the envelope estimations, throughputs, and so here basically this is very important to understand when it is not necessary. So this basically, it really comes up with trade-offs. So like assume like you're just choosing this approaches as strategies that we just discussed. You'll assume like you went with Q. This comes with trade-off is basically eventual consistency and delay and also that introduces that problem. Again, if you're choosing partitioning, the read path may suffer, and again you need to lay more focus on that. And if you choose a batching, it'll add latency and moving parts and all. And so always see that you don't really over engineer the stuff and all. I know we always try to end up in that situation, but better to avoid and mitigate wherever we can. And if it's a small scale, just stick with single dB, and that should be able to help with us. So because if you try to introduce this any of these approaches, instead of creating solution for our problem, it itself will become the problem for us. So that's the thing. So now let's just common scenarios, like for example, how do we handle resharding, like when we add more shards and all. Let's say like I try to increase 8 to 16 or like 16 to 32 and make sure that we don't have a node no downtime. How do we handle this kind of like things? So that's where we'll try to do an dual write to old plus new. And so what do? We try to do like multiple dual write to old shard as well as a new shard, and we'll try to read from the new one, and in the background processing we'll try to backfill from this old shard, and once we are done, we'll try to cut over, and this new reader will be reading it from the new shard. So that's like trying to do dual writes, and this way like we make sure that no data is lost, and also like and there's no downtime, and then we drop the old shard when backfilling is done. So that's like one of the usual migration, gradual migration to handle that kind of scenario. And now basically, and another scenario is like when we have a art key, that's too popular for even a single shard. So that's again we'll try to break down that key into multiple subkeys. So basically here, so we'll try to split that, like this is popular, like celebrity problem, like most popular accounts, like for viral tweet or viral video, or like which is receiving billions of views or something like that. So that's like considered as an art key, and then we'll try to again use the sub key and try to spread across multiple shards, so that the traffic will be distributed to that respective shards. So here the idea is that we'll try to split into k sub keys, and now basically now if writes is something, it is will be taken care. For reading, again we need to sum all of this the sub keys, whatever that we have. I'm mostly like writing the likes or comments or something that we split it. So for example, some reel is going viral, so likes we can split it something like this: additional sub keys 0, 1 or 2 and those things. Only thing is again to read back all the likes for that specific this reel, we need to again sum all of that, but again this is a trade-off for read thing. So because now if we split this, now each shard just takes 1/k of the write volume what was taken by this single shard. So that's the thing. And also that was like, splitting the key thing and the splitting key dynamically. That was like we decided that was the going to be harder, so we split it statically also. But the other situation is also like, we can break this hard key into sub keys, like based on like, we are seeing some pattern whether keys odd or not. For example, like I said, for viral tweet or so, we might split across like, let's say 100 sub keys and all, each handling like 100 likes or 10k likes or 1k likes. When reading, we aggregate those counts from all sub keys. So basically both of these approaches, whatever we just mentioned, so they mostly work for the metrics that can be aggregated, like, likes, views, counts, balances, but they don't work at all for anything that must remain atomic, or for example user profiles. So this is something we need to choose and adopt for the ones that really suits for. And here like, this writer will track which is hot, and then if it's cold, we'll just keep it in one shard. If it's hard, we'll try to do this subkeys split. So this is again we might have some logic within that time span, how many events it is receiving, or is it like, above the threshold that we have, then accordingly we can dynamically split by keys and all. So yeah, so that's the thing, the how we do this handling of these hard keys and all dynamically as well. So to conclude, this is basically only choose when it really solves our problem. Until then, stick with simple way, and and do not try to complicate and choose any of these approaches. So because the key insight for any of the approaches basically trying to reduce throughput per component whatever we have in our system. So and make sure that each one can handle the manageable load and all. So that should be our goal and insight whenever we are trying to discuss. This is all about the scaling rights pattern. Right. All right. Now let's discuss about very important pattern, which is multi-step processes. So this is very hard to achieve this and understand. So understanding it's very critical and to handle in distributed systems, because with the first-hand experience on real product development and on calls and all, we know what it takes to have a system and support this, and having ability to reset back and then try to have a workflows that can run for days and wait and all those things and all. So let's try to understand why, because why is it so hard to build in real production systems, because they must survive failures and retries and long running operations waiting for hours or days. So these are like this is what it's called through multi-step processes, which involves like coordination of multiple services and systems. So that's the challenges, so that's the problem. So let's try to understand basically what in the real world how it might look like. So consider an example of like simple example that we can all connect to: order fulfillment section. So let's say we have an e-commerce order fulfillment workflow. So what we do basically, usually charge payment, and once this payment is done, we try to reserve that inventory so that it will not be booked by others. And once we reserve that inventory, we need to create a shipping label for that, and then wait for some a warehouse worker or some delivery
candidate to pick the item, and we need to send the confirmation mail. Those are the series of the steps. So now you see that basically this is what I said, like charging payment and reserving inventory, creating a shipping label, pick and pack, and then send confirmation and wait for the pickup and all. So these are the steps, they're all tied up together. So assuming now even if one step fails in between, how do we handle those things? Okay, so here basically each step it involves calling different services or waiting on humans, basically humans in the loop, or any of which might fail or timeout. So and some systems, for example charge payment, we mostly call out to external systems like Stripe or also other gateways, and wait for them to complete. So during these orchestrations our server might crash or anything might happen. So now how do we handle this messy complexity of all this business needs that comes up in whichever the domain that we are trying to handle? So here we need to wait on this gateway, and here reserving inventory. If it's unavailable, again we need to initiate this refund, and if it's not able to create a label for that, if some machine is down and all, should we raise a ticket or so? And again here sending confirmation, it could take an hours. And here as well pick and pack, basically the pickup guy can come after an hour or so, or after a day, or after a few days, or whatever it is. An email failed, should we retry, and all those things. So these are like trying to patch each step. So we need to have mechanisms to retry and have the compensations actions that we can undo the thing that we just did using that step. And also we need to have delayed queues, and all these things basically are the steps. So how do we handle all of these situations is what comes in this pattern, multi-step processes. So mostly you will see this in these days with AI systems heavily adopted all these multi-step processes, and you will see every tool call approval or rejections and all those things, that's also step, and all sandbox agents, background agents, and in popular systems that we are already seeing in payment systems and in like Uber systems and all those things. So let's see how can we deal with this thing, how do we handle and all the solutions. So the solutions, let's try to see all the possible approaches that we can see. The first is basically single server orchestration. So the simple thing that we can do is try to orchestrate everything from one server, so trying to call each service in sequence. That's the only thing. So basically our the API server, the server, individual server that normally we usually start with, it will get an order from a user. So here we have it will get an order from user, and we'll just walk through steps in order. Basically what we do, we try to charge the payment and reserve the inventory and create a shipping label and send the confirmation email. So that's the flow it's going to look like. So the single server that we try to handle all of this for things, and payment service, of course will receive webhook response and all those things. But the problem is here, assuming everything is happy path, and we assume that we never have to do anything with scaling and all, this is exactly, it's a good path and to start, and we'll say okay, this is fine, it's working fine. But this has two serious problems. Reliability guarantees, that's one, and of like more complex coordination. So first thing is crashing and the failures. So what happens if this server goes down, the only one that we are trying to rely on? So maybe like let's say we charged payment, and before trying to reserve this inventory, that step server crashes, and now when it restarts, it has no memory of what happened and all again. So we charge the customers and we have not delivered any product and all. And this callback routing here, this webhook gateway payment gateways, basically we'll try to give them the webhook endpoint, so they try to hit our hosted endpoint, and then we know exactly when payment was successful and event change, and then we try to update metadata in our DB so that we know if the payment has been made or not and all those things. But here let's say if we have scaled out our the server, then how does it know to which server to send it to, and that callback can land on completely different host than the one that started the order. And now that host has no idea like which in-flight order the callback belongs to, and all those things. So that basically we can usually patch that up using this approach called PubSub, introducing that. So here we try to now persist the order state to the database. We'll maintain this order state DB after each step that we complete. So now no single host has to remember it exactly, and route callbacks through what we do. We try to do using this this webhooks or whatever it is through PubSub. And so whichever server is free can load that order and continue where the last one left off. So this would look something like this, trying to handle now with state, maintaining DB and PubSub for callbacks handling and all that stuff. And now we still have a few more problems to solve even with this approach. So with multiple API servers, who picks up the dropped work? Okay, so that's the thing. And also compensation is still unsolved. Like if inventory reservation fails, now we need to refund the amount, right? And even if shipping fails, we need to release that inventory reservation and all those things. Like the successive steps needs to undo the prior steps and all those things. So that is what it's called, the compensation actions or something of that sort. So where do we go from here? That's where like we have the patterns called the Saga pattern. So Saga is nothing but it's a detailed series of events, like that's where series of sequence of local steps where each step has a matching compensating action that undoes it. And we try to run the steps one at a time, and if later one fails, we try to walk backwards, firing those compensations to unwind whatever already happened. So that's the thing. And there are basically alright, so there are two ways to coordinate Saga, one through choreography and another through orchestration. The one that I really like and we adopted is orchestration. And choreography is basically there's no coordinator at all. So each worker subscribes to events it cares about and does its piece and emits new events for the next worker to react to and all. That is a classic example for event sourcing, which here I have listed down. We'll walk through that. And other is basically orchestration, so where a single orchestration owns the flow and tells workers what to do and all, because the whole sequence lives in one place. Now orchestration works best for very, very complex workflows. That's what the durable workflow engines like Temporal and all we are using, even I use extensively at work and all those things. Okay, so let's talk about event driven choreography here. So basically choreography, the thing is basically here I wanted to let's give you a brief thing, the source for that. So like instead of storing the current state, what we do, we instead store the stream of events that got us to that specific point that we are in. So then let workers react to those events to drive the process forward. So the most common way, basically adopted at work to store this durable log is basically Kafka is a popular choice, although this Redis streams could also work in places. So that's where event sourcing, that's closest match to that. So event sourcing, what it does, it tries to treat the log as a source of truth and derives state from it. So and here we are trying to use the log to coordinate work. So they basically often travel together but don't have to. So let's try to understand what this is. So basically here we have this client and API server, everything whatever we wanted to write, we'll try to write it to event store. So we'll have these topics, order, payment, inventory and shipping. And whenever we try to write event of the specific thing, the workers will automatically pick up and do the job. So here we have the payment workers, inventory workers, shipping workers, and everything happens. The event will trigger, will pick up this workers and does the job. So That's what this event store basically tries to take in the double duty. So it holds the entire history of the system, and also it drives the next steps. So whenever something happens that we need to react to, we write an event to the store, and these workers whoever are here, like ordinary services like processes, subscribe to this log, consume events, perform their work, and emit news events. So for example, if you take a payment worker, it sees basically order has been placed, so now and calls our payment service. So and when the payment service calls back later with the status, the payment worker whatever you have, it emits like payment changed or payment failed, and that will be seen by this inventory worker, and it emits like inventory reserved or inventory failed, and so on. So this compensation also flows the same way, just the backwards, so that now payment worker will also be subscribed to like inventory failed, and reacts by doing the necessary thing like issuing a refund and emitting payment refund and all. So here now you see here API server now is just the thin initiating wrapper around this event store, and when the order comes in, we emit an order placed event, and the system springs to life to carry the event through the system. And then rather than services exposing APIs, there are now just workers trying to consume events from our store. So this is a thing, and what we get out of this event sourcing pattern is basically gives us fault tolerance. So worker consume the log as long as they are actively able to connect to our consumer group, as a log, and they can do their process and all those things, and easily we can scale each individual worker. And observability, so the log itself is a complete audit trail of everything that happened. And flexibility, so appending new reaction is pretty easy since it's just new worker consuming existing events and all those things. But here what we do is we need to build the infra, the event store that I'm talking about, and the queues, and also the orchestration and the debugging event and all. Everything is pretty hard. That's again the trade-off and all. That's one way. The other is basically the workflow thing, the workflow orchestration. So here for orchestration, this workflow is basically a reliable long running process that can survive failures and continue where it left off. So this is basically is what the durable execution engines that I was talking about, temporal, like popular open source preferences. Everybody is trying to adapt into their systems, especially when AI boomed and all those things. Okay, so here basically we need to understand few things here. Durable execution is basically a way to write long running code that can move between machines and survive system failures and restarts and all. Like instead of losing all progress whenever even server crashes or restarts, this durable execution systems will automatically resume workflows from their history databases, like replaying events and all those things, and then resume from the step they are supposed to actually continue and all. So let's basically here that's what like workflow is durable, resumeable process, event sourcing plus state management, and no hand-rolled info and all those things. So here the best thing is it's like we write everything like code. So durable execution engines, like not like it's a declarative, it's a complete imperative, and greater control for developers whoever is trying to build the systems. So for example, temporal, and we have the here other managed workflow systems like step functions and airflow and all, which are not of greater flexibility, but that works. That's not my favorite and all, but both give durable execution and checkpoint each step, and can resume on a new host after a crash and all those things. So let's see now the example for the temporal. So we try to write the workflow as a code. The engine basically tries to replay from this history to recover and all those things. So here the important jargons that we need to understand is few things: workflows, activity. We need to understand what are they. So here let's take an example. Trying to understand workflow. This is the high level flow of like our system, and here activity is basically one step in that flow. So picture the, like, let's say we can picture workflow as completely the ordered steps and the decisions between them, and activities as simple individual actions that can touch the outside world, like calling to a DB or talking to payment external parties and all those things. That is the activities are what we can call. So, and one thing we need to understand is basically few principles. Workflow must always be deterministic. Basically, given the same inputs, we always get the same it takes us to the same path, and it always makes the same decisions. And when it comes to activities as well, it needs to be idempotent. So let's say if it's DB write or any other things, no matter how many times we do, it gives us the same result. So we need to make sure that what's the key that we are going to use and how we are going to maintain those things, so that it's safe to attempt retries. That's very important, right? So that is why, like, and why the determinism and idempotent that I'm trying to stress is here. Recovery, how recovery works is by replay. So every activity result is recorded into history database that will be managed by that temporal itself. And if a workflow, let's say the runner which is running the workflow crashes, then another runner re-executes that workflow function from the top. So every time the replay, it's an activity that's already run, the history hands back that result instead of running it again. That way, like, instead of running, we try to get the result from the history DB. And so because the code is deterministic and no activities refire or replay is that's what, like, gives us assurance that no side effect will be there, and execution lands exactly where it is left off and all. So that's the thing. So for example, let's take an example here, order workflow. So here we're trying to start the process payment, and it runs and it lands its result lands in history. And then the reserve inventory runs, and its result lands in history. And then server, let's assume that executing the workflow dies. So now what happens? A new worker picks up the workflow and tries to re-execute the workflow all the way from the top again. So now at the process payment, the history already has the results, right? So now engine returns it without calling the payment service again. So that's how, like, it tries to get from history DB. Same at the reserve inventory, and it gets it, and now it reaches the ship order, and it knows that we have not executed that, and now it continues live from that exact point that crash interrupted. So here now we are guaranteeing that the customers are charged once, the inventory was reserved once, and none of the business code that had to crash is affecting any of the workflow. So here basically, and also a very important concept here, the signals in a workflow will offer a greater flexibility for a workflow to wait for an external events. For example, let's say human in the loop, like human approval, or else like webhook listeners, and manual inspections and all those things. This is something that we can wait, and all those things and all. And here the temporal deployment, we need to understand what components that we have. So here we have few things. So the temporal cluster, we need to talk about this. So the things that you'll have is temporal server. That's the actual bookkeeper. So basically it hands out like tasks, tracks timeouts and records like progress and all. It doesn't run on any of our code. It's by default its functionality. And the history database, very important, the append only log of all workflows, decisions and activity results and all those things. And here we have workflow workers, basically the pool worker pools. This is where the processes that we run hosts our actual code. So the workflow workers, they run workflow function to decide what happens next, and activity workers that we have execute the activities and all, where they can talk to external services and all those things. So this is how it's going to look like at a high level. Overall, the temporal deployment is the thing. And so we have besides the temporal that I was talking about, and we have this managed workflow systems, though I have not used extensively, but the difference between that is, temporal and here is basically we try to define here the workflow as a state machine, okay, or a DAG in JSON or YAML in this format, this stuff. So AWS step functions and Google Cloud workflows. And basically if you try to do in this, the advantage is basically we can try to visualize as a diagram, which is a nicer UI to see, and also like it's less expressive than code, which is very bad thing. So and we don't have no flexibility, and again it's a deviation from the code and all anyhow. But these are all not handwritten, they will be generated by AWS CDK and all those things. But that's the thing. My favorite is temporal. And now let's talk about this the implementations. So which one to pick based on our preferences. So temporal is the most powerful one, like I mentioned. So it's a true durable execution. So here we can operate our own cluster in K8s and self-host and all those things, or else we can just use temporal cloud and all. But we mostly use self-hosting option, try to have manage in our own K8s. Another is the step functions AWS offers, which is serverless on AWS, and this is a JSON state machines, and it has limits and all, 1 year durability and 256 KB data payload size and all. And then these durable functions are in the Azure or the Google Cloud workflows, similar functionalities and easier to run than temporal infra overheads and all, and less flexible. And Airflow basically they are good for ETL tasks, extract, transform and load and schedule batch, not really for event driven programming. So default I would say stick to temporal, and others if you want you can just choose that. Okay, now the question is basically when should we use and when not to use. So whenever we see there is a state machine or stateful, then by default like we go for this is the multi-step process, a multi-step pattern, and then see if we can think in the terms of workflows or activities, and think of temporal and how can we act that as a gluing between of our all services and all those things and all. So that's the thing. So if sequence of steps needing a flow chart, then definitely that's a pattern, and we just try to use this workflow engine, like try to centralize state at one place, and retries and compensation, make sure that determinism and all the principles, activities and all those things and all. So yeah, so that's the point to look for. And now let's try to see few scenarios like deep dives and all. So here the most at least well-known examples is payment systems, because it has to deal with a lot of state management, like for example refunds and waiting for the approvals, and third party MasterCard or other things and all. So those states and all those things, and human in the loop, for example especially in the AI agentic systems, for anything that is destructive in nature and all, we exclusively ask for accept edits or approve or reject and all those things. Those are like patterns. And also like besides that, AI Uber or like rider waits for driver to accept that. So there's again human in the loop, again that's the multi-step pattern and all those things. These are all basically great examples or use cases for our the workflow related stuff. And so basically they shine wherever the stateful process must complete reliably or roll back cleanly, like all the way back to step 0 and all. So those things. And fine. And let's see now. So for example matching workflow, Uber matching. So what we do, loops over like nearby drivers until one accepts. So we'll have the rider service, driver service, and here assuming here we have the matching workers. So it will try to try to wait for this driver to accept and all. So here basically we try to propose to nearby drivers one by one, and on accept we try to notify the rider, on reject timeout, and we'll try to try the next. you see here, we can now use the standard code looping of the drivers list and all normally into our code as a workflow, and this is a great flexibility for the developers, right? So that's the thing it provides, and that's the just the example. And when not to use and don't even think about is basically if it's a simple asynchronous processing, straight away big no, and we can just straight away use a message queue and all those things, for example resizing an image or sending an email. And if it's a like a synchronous operations, so if a client waits for the response and there's a lot of sensitivity around latency and all, you never even think of this multi-step process. And same thing, high frequency and low value operations workflows, they really add over it, and there's a big no. And these are the situations like big no for multi-step processes, and don't try to adapt this pattern and all. So now let's try to see few situations. So updating the running workflows. So here's the situation. So basically let's say we have like 10,000 workflows are running and mid-run, and now we need to add new step. So how do we take care update these things? So first approach is basically versioning concept. So here what we do, we try to deploy a new version separately, and old runs finish on the old code, and simple, and basically there's no in place change and all. This is like safer bet. And other is basically migrations. So here this is a pretty complex. So what we do, we try to update the definition right in place, whatever we have, and then we have a concept like called patch to branch deterministically. So this is how, like for example, we check here this patch to call whatever we have returns true for new executions, so they run this the new behavior. So the executions whose recorded history already extends past this point from running the old code and all, it returns false, and it stays on the legacy behavior whatever we have. So that's the thing, versioning and then migrations to see if we wanted to add new step for the existing ones, and how to adapt the new path and whole path. And that's one thing. And the other situation is how do we make sure the workflow state is small. So here basically we know that durable engines process the whole history and replay it, like states can like very fastly balloon this. How do we handle? So always try to keep the input as the shorter, trying to pass in the identifier, so that we can use that to look for that in the DB, or if it's a file path, S3, pass that instead of the actual bytes, and then you can get the file in the activities logic and all. Or if it's a file system that we are talking to NFS and all, pass the path and try to read in the activity logic and all. So that's the thing. Not payloads, and we try to store big data in DB or external, and we'll try to keep the activities inputs and results small. So or else there is a concept called continue as new. So we try to basically periodically snapshot a long running workflow, and try to add a fresh copy to a new temporal workflow, and we try to continue as new from that state, instead of all the way starting from the step 0. So that is the two ways, continue as a new, and make sure that passing identifiers are not payloads. So that's the thing. So we try to keep smaller activity input and output, and the periodic recreation keeps that replay fast and history bounded. So that's the thing. Okay, fine. And the other situation is how do we deal with external events, and how do we wait for it? And this is where the important topic that we need to be at least aware of, signals. So we need to wait for human or webhook for minutes or days without consuming resources. And let's say for example we are waiting for signature and all, so we can wait up to wait for a signal like up to 30 days or so, instead of relying on the polling and all. So in that case what we do, we try to define a signal and set handler to that, and basically create one variable and try to set the data in the callback, and we then put a condition, call the condition until the signature is not defined, wait for this 30 days, and if we don't get still after even 30 days, again set a reminder for that document ID, and again wait for 7 more days, and if not, we can just cancel. So that's the thing. This the process signature and all. Then this basically what signals do, they suspend the workflow efficiently, so there's no polling, no resource use and all, and this way, like, we are not awaiting on a thread or blocking a thread or CPU consumption and all those things. So that's the thing. And the how do we ensure that no matter how many times we retry, that impact of that step is the same. So how do we ensure? So that is the thing, making it an idempotent. So idempotent is basically the key should be very unique, like for example email or and also have the picked by that activity by checking on the status, like after completed, like if it's completed only try to pick it up, and so that's trying to make the idempotent and store an idempotent key, and we try to even check before the reversible action. So that's the thing, so that we ensure it's all atomic and all. The why the status maintaining is also needed, like it's completed or in progress and all. Let's say we are trying to do some shipping and all, and that process can die after maybe charging payment and all, but before recording that actual idempotent key. So in that case, that is where that marking that key as in progress or completed really helps, not just the idempotent key and all. So this is what, like before sending, if keys email order 1 2 3 already exists, we skip, else send, then store the key. So that is the overall thing, this multi step processes and workflow, durable, engine, temporal and all those things. So conclusion is basically this. So workflows engine helps us to turn the fragile manual orchestration into this robust observable process. So look for these things. If we are hand rolling state, retries and compensation, then that's the definition for workflow, and just try to adapt to this temporal also. And durable execution code example, temporal or managed, we have two ways, and prefer the way that your stack really adapts to, and they survive crashes and deploys and checkpoints, replays, resumes and new host and all those things. So we have like signal for workflows. So undo step 5 if X fails, or all steps complete on undo. Okay, so this is the conclusion and the learnings from this pattern. And yeah, hope you get the intent of this pattern, and know at least now where to use and all. All right, now let's talk about how do we manage long running jobs. So the basic idea is like this is a pattern where we try to split API requests into two phases, like immediate acknowledgement and then doing heavy job in the background processing and all. So basically, if they submit heavy tasks like let's say AI video generation, or like agentic processing behind the scenes and all, then the web server, what it should do, basically ideally it should immediately validate the request and push that job to our queue. It can be temporal, anything AI agentic workflows or Redis RabbitMQ or Kafka, whatever it is, and return the job ID all within milliseconds. So meanwhile, the separate worker which will be polling over that respective task queue will grab the pending jobs and execute the actual time consuming work and update the job status in the database and all. That's the usual pattern. So let's see. Okay, that's the thing. And fine. So here the problem, let's try to understand what is the problem, for example. Okay, and I'm just going to zoom out a bit, maybe, yeah, this should do it. Okay, fine. The problem, so imagine we are running a product where users can maybe
ask AI to generate something, image or video or something. So whenever user tries to submit a prompt, we try to make a call to our AI, and the whole process of taking in a prompt and hitting our servers and delegating that to GPUs where our AI models is running, and then the whole process like querying and then processing, generating and all, it might take few seconds. Okay, so in that case it's not ideal user experience that he has to wait maybe 10 minutes, 20 minutes, 30 minutes or like an hour or so, depending upon the heaviness of the job. So if we are trying to do this kind of heavy jobs in synchronous processing, that's very bad. That's the problem. So if it's, let's say it's a simple thing and I'm just trying to load some content of my article or so, that's a simple, it just takes roughly querying the database and then formatting the response and sending it back, and you will see what the article content is, something like that in website on your product. That's simple thing, that those kind of things that we can handle. But these heavy kind of things is something we cannot, and it basically takes in a lot of server processing time and all. So let's say here this any example works, so waiting for like minute or so, it really doesn't help, and that's the problem. So how do we handle this is the thing. So and also like most of the servers and load balancers enforce timeout limits around like 30 to 60 seconds, so the request might not even complete, forget about the bad user experience and all those things. So how do we deal, what is the solution is something that we need to understand here. So the problem is basically asynchronous worker pool. So now basically instead of making the user wait while we are generating some video or like any agentic processing and all, we try to split into like two parts. So the idea is to decouple acceptance from processing. So what we do here, we immediately like let's say when they say like generate video, we immediately store their request in a queue and return a response that like, yeah, we are generating a video or image for you, so we'll notify when it's ready. Like this takes some minutes or so, something like that will showcase in the UI, so that it will be better user experience. So now the web server job is pretty simple and straightforward. So what it does, it just validates the request and adds it to the queue, and then returns the job ID, and the actual the image generation or video generation happens somewhere in this heavy workers, maybe GPU workers or whatever it is in K8s or any infra that we have, and it does every job and all. Once it's done, it will just try to update the status in DB and will notify through email, push notification or WebSocket or whatever it is. So that's the solution. So decoupling acceptance from processing and accept fast, and we try to work in the background and notify when done. So that's the the solution that we'll be trying to lean towards, and that's the thing. And this separation basically helps us to solve the problems of how can we independently scale. So first thing, independently scaling, let's say now web tire and workers, since they're decoupled separately, and they can scale as the traffic goes up, and the cheap web servers just handle the request and then acknowledge that we have received a request and we are processing in the background and all. And like let's say the heavy GPU workers, video processing and all these AI generations and all those things can be delegated to GPU workers. And then this solution of detaching things helps us to achieve this independent scaling very the affordable one. And here now, once we choose this, there are some trade-offs that we need to see. Once we choose this detached separate pools, asynchronous worker pools, we have this fast response. Like we straight away return that, yeah, we acknowledge we received your request and we are processing that, so there's no timeouts and all that stuff. And again, independent scaling that I just mentioned, so each component can scale apart. And fault isolation, so any one worker crash cannot really bring the old system down, down, and it doesn't kill the API which is running in a web server, and new worker will be coming up as soon as the other worker is down. And better resource use, so basically we can know how many instances or workers to configure specific task, and so workload wise we know which one to scale and all. See, but the what we lose here is basically complexity. Of course, we need to now worry about queues, workers, status tracking, the infra for that and all, like distributed systems and all those things, and eventual consistency. So how do we sync the data across our all systems, and so that it is consistent what we are showcasing to the user and what's happening in the background and all that stuff, and the status tracking. So yeah, here we'll try to see like poll for status or more DB load or API service, and monitoring, so worker health, failures, and all those queue depth and all. So but this the trade-offs that we get looking at what we lose is very minimal. So this ideally that's very negligible. That's the thing. And now basically what to how to implement. So there are like two critical things. One is message queue and another is a pool of workers. So message queue is basically a system that allows us to send and receive messages between different parts of our system. So these days extensive usage I see, at least people using, is temporal, whenever the AI agentic processing and all happen. So that's like providing a best way to in like as an infra for background jobs and agentic processing and all those things. So to talk across the systems, there is a queue to queue communication and all very beautifully architected, and that's how they decouple the sender and receiver of message, allowing them to operate services independently. And then the pool of workers, basically it's a group of processes that are dedicated to processing messages from a particular task queue and all. So they will be polling that specific task queue. Whenever we have a message, it will try to pick it up and process whatever it is. Let's say it's processing heavy AI of like parsing, classifying, and then going through our list of domain logic, or else like let's say if it's running some heavy automatic RPA tasks on VMs, on Windows VMs or all something like that, this dedicated workers they can try to have, and they'll be polling that respective queue. So now let's talk about this implementing message queue. So here the queue needs to be durable. So basically even if it crashes, we need to make sure that we don't lose all pending jobs. So, and it needs to handle concurrent access from multiple workers without duplicating work. So there are a few things, bull MQ and Redis. Basically that's a simple memory first and can lose jobs on crash, because Redis is still the memory first. So that's one option. And then AWS SQS fully managed, and it's like and also paper message, so which is great at low volume but can get expensive at scale. And also we have 1 MB message size limits, and that means we need to store job data elsewhere and just pass the IDs through the queue and all that stuff. So that is this. Another option is RabbitMQ, and this gives us more control with complex routing patterns, but again requires self-hosting and infra configuration and all that stuff, and monitoring upgradings and managing clusters and all those things. And other is basically heavily adopted is the Kafka. So basically when our stack already is like using event streaming, it's upon only log lets us like replay messages, fan out to multiple consumers, and it can help us to keep data around for long retention windows, while it's built to handle huge volumes with strict ordering guarantees and all. And again you can add temporal as well. That is also one of the things that we can use. And now coming down to workers, so here workers basically they are servers which tries to I mean at least to say in simple terms, so they pull jobs from the queue and execute them whatever the behind the scenes that specific domain logic or that is supposed to handle. Okay, so the key decision is basically how do we run these workers. So there are ways like normal servers. Okay, so here it's basically simplest. we run like 10 to 20 workers, let's say full control and easy to debug. If anything is going wrong, we can just SSH into it and understand what's happening. If there is something that we can manually interfere and then get it working or something, and it easily handles long jobs fine. And the thing is, basically, even though it's not needed all of these instances, we need to pay for the idle capacity, this normal servers. The other way is basically serverless functions, Lambda or Cloud functions. They completely eliminate our server management. So each job, whatever it is, triggers a function execution that scales automatically. Like like this is mostly works pretty well for spiky workloads, where we might need to process like, let's say, 1k jobs, 2k jobs per minute, and 0 the next and all. So now we are trying to actually pay for the actual execution time, and again we are limited here 15 to 60 minutes executions and all, but we need for hours and all. This is not the way to choose. So that's the serverless. And other this containers, K8s or ECS. This is mostly what we prefer at work and all those things. So here what we do, we try to package workers, all the logic and all, as a Docker containers, and let the orchestrator handle the scaling and deployment. So this is what mostly ideally adopted, though it's complex, but it comes up with the trade-offs again, which is what highly adopted. And this is the way to configure the workers, container based workers. And the worker loop will do something, it will be polling all the time for the queue, for that queue that it is responsible to pick the tasks from, and then take that and then process it and mark complete that job or somewhere in the DB and all those. So putting it all together, so this is how this is going to look like. So the web server now, all it does is basically validates the request and creates a job record in our database with status as pending and all. And then this web server, what it does, pushes the message to the queue containing the job ID, and then this web server returns the job ID to the client immediately. The workers, whatever they are polling this job queue, will pull from this queue, fetches job details from this database, and then this worker updates this job status to processing, and now this starts performing the actual work behind the scenes. And then it stores the results, maybe depending upon if it's a files, S3 compatible storage, and metadata in database and all that stuff. And then finally it updates the status to completed or failed at the end. And after that is done, we'll be notifying to the client in the form of the email, push notifications, or WebSocket, whatever the way it is adopted. So that's how basically we need to handle the long running jobs scenarios. And this is pretty much pattern we observe in any of the systems these days, whatever we are trying to build. So ideally, when to use this pattern is basically we know that if we see slow operations, for example, video transcoding, image processing, PDF generations, bulk importing, exports, heavy works and all, then that's the signal that okay, now we need to think about this long running tasks and detaching the processing and acknowledging things. And also, like if the amount of traffic that we are receiving and all, it really doesn't fit per server. Like let's say like we have like 10 million images per day, like for 10 seconds it's like let's say 120 seconds of work per second. So WebTire cannot really handle this kind of traffic. It saturates immediately. So that scenario, it's something we need to think of this pattern. And different hardware needs again. So AI and model related, it needs GPU or ML work. So that shouldn't share the work with the servers, which is just the login request that is our web server and all. So in that case, again, think about workers, configurations and all, and scale and failure questions. So server crashes mid job and all, then that's definitely scenario because of that heavy work, it's bringing the whole system down, and its API requests are also not getting handled. Then that's the thing, we need to now completely detach from the web server. So that's the thing. The idea is simple: return a job ID and processing async keeps in the WebTire fast, and now workers can do the whole heavy lifting and all. So this is the simple pattern. And now let's examples. For example, video platform, the scenarios like at least transcoding to 1080p
720p, 480p, 4K and all, like thumbnails, captions, generation or moderation. This can be, it's a huge the long running job here. That's the thing. Photo sharing, if they share, if they add some filters, resizing, metadata, image recognition, and then feed it, fan out to all these followers and all, that's the like heavy job as well. Ride sharing, like ride matching, route scale, route calculation, pricing, driver location updates and all should happen in dedicated workers. Same for payments and file syncing and all those things. So these are like few of the patterns. And again, these days AI agentic, like running cloud agents, sandbox configuration, having our own infra, and all those remote code execution of GitHub, like trying to do all this heavy PR task and all those things. Those are also like very good examples of this pattern. Okay, fine. Now let's try to see a few of the scenarios how can handle failures. So handling failures, so let's say like what happens, like if our worker crashes while working the job. So so basically the in between the worker job, whatever it was processing, it is crashed. And the idea is to basically we need to have a mechanism where it can detect crashes via the heartbeat or visibility timeout. So let's say we try to handle this situation by using the concept of heartbeats, like every 10 seconds or 30 seconds. So if it's not responding, then we know that has crashed, and then we need to redeliver, and the worker to others, whichever is available, will pick up the job. So if it's too long, we try delayed retries and all those things. So this is like the mechanism we should always have to detect these failures. And now trying to repeated failures, let's say like let's say job we are trying to retry, but it keeps failing. So there might be bug in our code or bad input data that is not expected to be sent to that workflow or whatever it is. So it gets retried forever, and our workers might waste cycles on this poison job and all. So for that case, how do we avoid is like introducing a DL queue. So this basically after let's say n retries or some failures, we try to move it aside. Like let's say we tried it 10 times and it failed, and then we know it has met this number, and we just move that one to our the dead letter queue. And then we can manually go on and inspect, and it will not be picked up by the worker anymore. So worker will automatically put into this DL queue after nth failure, and that's how repeated failures is the way handling using DL queue thing. And now the other scenario is basically how do we prevent duplicate work. So basically idempotency is important here. So basically like let's say I'm trying to click on multiple times to generate video or image on the UI, that like 3-5 times instead of me trying just for one time. Now we have 3 identical jobs in the queue. So how do we prevent doing the same work multiple times? So without proper deduplication and idempotency checks, we really waste resources processing these identical jobs. And let's say like it's like deducting money or sending emails and all that's going to be very problematic. So that's where we need to use idempotent keys. So like try to dedupe with an idempotent key before enqueuing. So here what we do, when accepting a job, so basically we require unique identifier that usually represents the operation. So for user initiated actions, maybe we try to combine the user ID plus action plus timestamp, likely like rounded to the duration, so that we prevent duplicate work. And for system generated jobs, we might use deterministic IDs, for example temporal workflow IDs and all those things. So before starting work, we check if the job with that key already exists or not. So if not, we'll try to enqueue into the queue and workers gets picked up. So that's the like trying to prevent duplicate work. And idempotency is very important in the operations or workflows, which is very expensive, and it will be very hard to revert those things. So fine. And then how do we handle queue back pressure?
So basically, let's say it's a flash sale, so it's going on, or year end or something on our platforms or whatever it is, some consider everything. So assuming we are getting 10 times more jobs than usual, so our workers are not able to pick the task. So basically the queue size is growing to millions and all. So when workers can't process jobs fast enough, the queue size goes unbounded, so memory usage and all explodes, and job wait time stretch like from minutes to hours and all, and new jobs gets rejected because the queue is full and we are no longer taking it in. So this is called back pressure. So what we do now, basically when workers can't keep up and the queue grows unbounded, so we try to push back, and in this case will not accept any more jobs when workers are overwhelmed, and we try to set the basically the queue depth limits, and reject new jobs when the queue is too deep, and we return saying that system is busy now, can you try it some other time and all. So you might have seen this in our your Claude or ChatGPT or Codex or anything, usually whenever you're trying to use those things. So and that's the thing. So back pressure handling and queue depth limit is basically we try to use, and then we can auto scale based on the, if let's say if queue depth has hit this number, so we add more workers so that it can pick it up. But that's how handle this queue back pressure. And the other, now how do we handle mixed workloads? So basically let's say there is in bulk imports or PDF generation, it might take 5 seconds or so, but if he's requesting for end of the year reports, that might take 5 years, 10 hours and all. So and they're all in the same queue. So now we are having the workloads which can take 5 seconds and which can take 10 hours or so. So we have mixed workloads. So now the long jobs, what can do, it's basically blocking the short ones. So how do we handle this? So here we need to now think of splitting queues by duration. So that's the idea. So fast versus slow jobs. So the fast jobs will just try to put into fast job queue, and it gets picked up by the worker, and slow job will try to put in slow job queue. So like this, so we'll try to have different queues. The thing, basically idea is to have separate queues by job type or expected duration. This is all well-known calculator and all, and only when we know all of this we can configure this fast and slow job, and we can configure max duration, worker count, and instance type and all those things, and it really helps. So that's how we try to handle mixed workloads. So that's the these are the scenarios and all. We need to keep thinking edge situations and all, and always try to come up with a better way so that our system is more always reliable, and it can handle all of these scenarios and all. So and then orchestrating basically job dependencies. So let's say let's say if generating a PDF or something, video or so, requires 3 steps: fetching data, generate PDF, and then email it. So here we have an interdependency between them. So without proper orchestrations, we can end up very badly. So let's say workers complete step 1, then directly queue step 2, making the flow hard to understand and modify, right? So here what we do, multi-step jobs, we try to chain them or use an orchestrator. So that's the solution. So here each job might carry workflow ID, the step, previous steps, context. So steps retry independently, and this is exactly where the temporal really shines and extensively used, AWS step functions or temporal or airflow and all those things. So that's the thing. So that's the thing. So we need to properly chain them with parallel steps, and then these tools basically helps us to define workflows as code, and it'll have retries per step and provides visibility into where workflows get stuck and all, and then we can reset from that step onwards in temporal UI and other stuff. So this is basically just more additional complexity. Now basically we need to manage our own infra and all this orchestration and all, where this job dependencies might become truly complex and all. So that's the thing, we have this separate pattern and all in itself, like multi-step processes. How do we handle, we'll discuss there. But ideally this is the conclusion when we should use async workers. So it's operation request. So if it's like, let's say greater than 5 seconds, yes, we need to consider asynchronous workers. If it's not, again check if it's a CPU or GPU intensive. If the answer is yes, go for the asynchronous workers, and if it's no, then do not go for it. And if we have high request volume, if it's again yes to this question, go for asynchronous workers. If it's no, just stick to simple server. And we have an external API rate limits that we're trying to rely on, for example this Anthropic Cloud and heavy API rate limits and all those things. So you can directly go for asynchronous workers and all. And if it's no, stick to the simple server. And fan out too many users, yes, go for asynchronous workers. If not, stick there. And if we need special hardware like GPUs and heavy machines and all, then go for asynchronous workers. And we need progress updates and all those things of every step that we are trying to do in the background and all, then you need to go for asynchronous workers. So if no is the answer for all of these questions, so be synchronous, simple architecture, immediate consistency, and less monitoring, and no job blocking and all, and less headache. And if it's an yes, then here we consider asynchronous workers. Like we'll have faster initial response and independent scaling of each of the component, and each of the team can handle their work independently, and fault isolations and also the progress tracking and all those things handles. So this is the handling long running jobs pattern is all about. And now you should get the decent idea like when to consider this pattern and when not to consider, and how does this work at a high level and all. All right, let's talk about real-time updates pattern. So just to put it, what does that mean in simple words? Basically we know that trying to handle the situation of like delivering immediate notifications to the clients. So like whenever the data changes from server to clients as events occur and all. So take an example of chat applications, like where messages need instant delivery, and to live business dashboards or game dashboard leaderboards are like trying to show real-time metrics, and their user expects like the experience to be notified when something happens. So this is the that pattern is all about. And first try to understand what's the problem, and then and once we know what's the problem, how can we deal with that problem and all. So the problem, so let's try to zoom out. Yeah, okay, fine. The problem, let's take an example, the applications that we use, maybe a Google Docs or anything collaborative stuff and all. So whenever, let's say, we are trying to collab on some pitch deck or whatever it is, like when user types some character, and all others basically are trying to view the document or so need to see that change like within in like milliseconds or so. So in apps like that, like we can't have like every user, like out of hundreds or thousands of users, constantly polling our server for updates every few milliseconds and all, because that's going to crash our infrastructure for sure. So that's the core challenge here. So how do we deal with that? Like establish the persistent connection channels between clients and server, and because we know that standard HTTP what it does, it follows the request response model. Basically clients ask for data and servers respond, and then the connection closes. That really works great for our traditional APIs and like browsing and all those things. But when we wanted the servers to proactively push updates to clients, that doesn't work. So that's the thing. So that's the problem, that like trying to understand in that applications, how do we deal with that. So that's why we need persistent channels and clever way of polling, so that servers can push to clients. That's this problem that this pattern really helps us to solve this. So let's see the solutions. So how can we deal with it? So let's try to break down into this two things. The first is basically the how do we get updates like from this server to the client, and the second breaking point is basically how do we basically get updates from the source to the server. So how does this server get triggered when something happens, whatever the core domain logic or that application is really dealing with. So let's try to break this and try to see how can we achieve each step, and see what are the ways to overcome the problems that we have. So before going to that, it's important to understand a bit of jargon of networking. Just I'll quickly open that. So basically the client server connection protocols, we need to understand that, and I think if you recall computer networks and all, we the architecture OSI model, so open systems interconnection model, so it has 7 layers, the application layer, then the presentation layer, session layer, transport layer, network layer, data link layer, and physical layer. So we have like 7 layers and all those things, but out of all those things, these 3 are the mostly important whenever you're trying to build a system. The thing is here, the application, the layer, so that is where like actually apps speak. So the DNS, HTTP, WebSockets, and WebRTC, so that's the like final layer. So I'm trying to come from the border or top down thing. So this is where like where we have these common protocols that build on top of TCP, like to provide kind of like layer of abstraction for different types of data that will be typically associated with the web applications and all. And the other layer 4 transport, where we have the TCP and UDP. So they like provide end-to-end communication service. So here basically TCP is more or less reliable and ordered, so that's connection oriented. So before we try to send a data, we need to establish a connection with the other side. So once the connection is established, it ensures that data is delivered correctly and in order. So that's like assures greater guarantee, and also at the same time we should be aware that it takes time to establish and resources to maintain and bandwidth to use. And UDP here is basically it's a connectionless protocol. So we send data to any other IP address on the network without any prior setup and all, and it does not ensure that data is delivered correctly or in order or so. So that's the layer 4 transport where the things handle. And layer 3 is the network thing. So here this layer is basically routing and addressing. So the protocol basically that's where like handles all of this routing and addressing, and it is where we try to break the data into packets, like handling packet forwarding between networks and providing best effort like delivery to any other destination IP address we have on that network. Again, there are no guarantees packets can get lost, duplicated, or reordered along the way. So these are like at least the layers that matters, and we should have an high level idea of this, what happens at each the layer that we have. And so because they all like build on layer the below that it is present. And let's see now and before so how does request lifecycle work. So basically whenever we type something example.com or so, what happens and all those things and all we'll see. And before that, let's try to understand the transport layer, what's the difference between TCP versus UDP. So we know that both carry data end to end, and just to understand, this is connection oriented. So handshaking is must before we send, and it is delivered correctly and in order, so there's a guarantee that it gets delivered. And it costs because setup time and also resources and the bandwidth and
latency thing. And this is the by default, that's what like web users, and because it's reliable. And UDP is completely connectionless, so it sends to any IP, no setup is needed, and no delivery or order guarantee. And it's like, send and pray that it gets received by another IP or so. And it's a lower overhead and pretty fast, and it's very good for loss tolerant streams and all those things. Okay. Yeah, that's the brief difference between TCP versus UDP. And now let's try to understand the the request lifecycle, how it usually happens. Like whenever we type in the URL into our browser, then this several layers of networking protocols will be into action. Let's break down how this basically those layers work together to help us retrieve that simple web page or HTTP, whatever we are trying to browse. Here first, so I'm just trying to this is like the network layer, transport layer, and this application layer. Just understand this the way. So first what we need to do is, like, we use DNS to convert that human readable, whatever the domain we have, like example abc123.com or something like that, into an IP address like some say 100.0.0.1 or something like that. And so here let's what we do, we break down that, and then series of steps. Like I said, the DNS resolution. So this client, what happens basically, resolves that domain name and gets an IP address. And once we have this IP address, the first step is this TCP handshake. So this initiates the TCP connection with the server using this three-way handshake. So first is the synchronized thing. So the client, whatever it is, sends this synchronized packet to the server to request a connection, and then this server basically responds with synchronous and acknowledge packet to acknowledge that request and all. And this client sends an acknowledge packet to establish the connection. So these are the three steps where now the actual TCP connection now gets established. And after that, the actual HTTP request. So once that this TCP connection is established, so this client sends an HTTP like get request to this server to request that whatever the content of that web page is. And then this server processes that request, retrieves that web page, whatever it is, and prepares the response, which is the HTTP response. So it sends the HTTP response back to our client, which includes that content of that specific web page content, whatever user has requested for. And after that is done, so this is a TCP teardown. So basically once that data transfer is complete, now the client and server close that TCP connection using a four-way handshake. So first this the client sends a FIN, so which is a finish packet to the server to ask it to terminate the connection, and this server acknowledges that finish packet with the acknowledge thing, and then it sends the finish packet to the client to terminate its side of the connection. And finally again this acknowledges that server's finish packet with an acknowledge and all. So that's how, like, with a four-way handshake we try to close the basically TCP connection and all. So this is the thing. So basically what I wanted to say is, like, each just to understand high level is there is a round trip between client and server to every request, including to establish connections before we send our application data. So that adds a bit of latency. And also, like, this TCP connection itself represents state that, like, basically this both client and the server must maintain. So and that's the thing. And just to understand what happens, how TCP connection work and all, that's the thing. And now let's understand something about the load balances. So in typical systems that we build, Ideally there will be multiple servers like working together behind a load balancers. So this load balance, what they do, they distribute the incoming request across these multiple servers that we'll have, to ensure that even load is distributed, and we guarantee high availability or something like that to end users. So there are basically two types of load balancers we need to understand. One is layer 4 and layer 7. So I think by that number itself you should be clear. So layer 4 is at the network thing, and layer 7 is at the application layer. So we need to understand when to use layer 4 and when to use layer 7. So for that, let's understand. So first the layer 4. So they basically operate at this transport layer usually, like TCP or UDP, and basically they are responsible to make routing decisions based on network information like IP addresses and ports. Like that's where, like, this is where we use to block requests from this IP range, domain range, and all those things, without even worrying about what's the actual content of the package that we are getting and all. So that is this very good example is NLB in AWS, network load balancer, and this is like is basically this helps us like make it look like we have selected random backend the server, and assume that TCP connections were established directly between the client and server, and that's the thing. So that is this layer 4, just to have a high level understanding of this. So, and to understand the key features of layer 4 is basically it maintains the persistent TCP connection between our client and server, and it's fast, and because there's no packet inspection, the actual data content, we are just blocking on the IP and the ports, and it cannot really make routing decisions based on application data, like if you wanted to restrict based on our logic of the applications or anything. This is not the layer that we need to use. And so that's this layer 4, and to put it in simple words, this is what is well suited for our WebSockets whenever we wanted to use WebSockets in our system. And that's this layer 4. And let's understand the layer 7 thing. So this basically operates at the topmost layer, which is the application layer, and this basically understands the protocols like HTTP and all, and they can actually inspect the data packets and all of each request, and like they can make more the intelligent routing decisions and all. So this basically at the HTTP layer, and that is basically at the layer 4, the TCP or UDP layer. And this again the difference of this again is can route based on this request content, actual URL, headers, cookies, and all. And also this is more of CPU intensive because we need to do packet inspections, and they again provide more flexibility and features to block anything, and they are basically suited for HTTP based traffic, similar to like API gateway. So that's what you can just imagine. And and they again so they terminate basically every request incoming connections and create new ones to this backend server and all. So this is important to have an understanding between layer 4 versus layer 7 load balancers and all. And now this should have given us like decent idea of the networking things and how do they work on top of each other and all those things. So once we have, now let's try to check on the ways now we can deal with for the first step that we have divided into, which is like the server to clients handling. So straight away, a simple thing that we can think of is simple polling. So this is the simplest possible approach. So what we do is just we'll have the client regularly keep asking the server, do I have any updates or not, and all those things. That's simple HTTP request, like trying to wrap inside this set interval stuff. And this is how, like, every 2 to 5 seconds we try to ask the server, and it repeats and all. So this is a simple to implement and also stateless, and no special infra is needed, and quick to also like implement as well. But again this what it the downside of this is higher latency, so we need to wait for the that interval to see what's the update from the server. Also more bandwidth, so usage, because we are making a lot of requests, and if we have many clients trying to take an updates from server, it can be very resource intensive, and because we need to establish new connections and all. So this is a good starting point. We can consider if it's the what solves the problem of our system that we are trying to design. Trust me, this can be the very simple solution than we thinking about the complex ones, because with experience, as we scale our system better, it's important to keep our architecture or as simple as possible, because we don't want to spread this state across multiple parts in our overall system and all. But this is one way we can straight away think of this simple polling. And now the other approach is that we can think of is long polling. That's the simple upgrade to the above the simple polling that we have. It's just what the idea is. Basically we need to make the server hold the request open until the data is ready, so then the client immediately re-asks us. So the flow is simple. The client, whatever we have here, it makes this HTTP the request to the server, and this server now holds the request open until any new data is available, and then server will respond with the data whenever the data is ready, and then again client makes a new request and the process repeats and all those things. So this is again just implemented a standard HTTP, pretty easy and stateless server side and all. And the problems with this downside is again same HTTP overhead and extra latency and burst, and hard to basically monitor, and by default we have per domain connection limits on browsers and all. So it's suggested to choose for infrequent updates. So like for example long async process, let's say like tell me when this finishes and all, like payment statuses or something like that. So that's when this is preferred. And if you choose this, the issue that comes with this is basically the biggest issue, long polling latency. Let's take a scenario here. Let's say we have updates arriving, like let's say like we have two updates, 1 and 2, like which occur like within, let's say 10 minutes of each other. And now with long polling, the first update basically here the request that we are trying to send like takes a latency of 100 milliseconds after it occurred. Basically that's the 100 milliseconds of network latency. But how this second request, the update may take up to 300 milliseconds after it occurred, because we need the first request to finish, and that's the the time it needs for the first request to finish and return that response, and then the 100 more milliseconds for the second request to be made, and another 100 milliseconds to get the response and all. So basically what I'm trying to say is whenever there are two updates like overlapping and all those things, the latency will keep piling up for the forthcoming request that it hits and all. So the waiting time it's going to be very unpredictable, and so the first request lands in somewhere 100 milliseconds latency, and then the second one can go again 300 milliseconds or so. So this gapless re-request keeps piling up, and that's the problem that comes with if we try to adopt this long polling frequency. So that's the thing we need to keep in mind, and decide when to use polling and all, and then see if that really makes sense for us or not. And the other the approach now is basically server sent events. So this is one way stream. So this is simple extension on the long polling that allows basically that allows the server to send a stream of data to the client. So normally this HTTP responses will have an header like content line, like basically which tells the client like how much data you can expect from this and all. So now this SSE basically it uses special header, the transfer encoding with a chunked. So basically what it tells the client is that it now the streams the response in series of chunks. So basically we will not know exactly how many there are or how big there are until we send them. So this basically allows us to now move from this single atomic request response to more granular stream of data. So with SSE, that's the thing. So instead of sending a full response once data becomes available, the server, what it does, basically sends a chunk of data and then keeps that request open to send more data as needed. So this is a perfect thing for the AHR application that like as tokens get generated from GPU, the models and all this, they'll stream these chunks of data and all those things. So that's how it works. This client, this establishes the SSS connection, and the server keeps this connection open, and servers keeps sending these messages when the data changes, and client receives updates in real time. So that's the thing, the simple thing. And we can use the event source which are by default built into the browsers. And the advantages that comes with this approach is basically they are built into browsers and automatic reconnection, and it simply works on HTTP. No new infrastructure is needed, and it's more efficient than the other approaches that we have just discussed, and also it's pretty simple to implement. And now the disadvantage of this is basically this is one way only, so sending from server to clients, and that's the first breaking the point that we are even trying to discuss as well. And limited browser support, and though it's not an issue in a modern browser that we normally use, Chrome, Edge, or Safari, or whatever it is. And and makes this monitoring, and also we'll have the per domain restrictions, connection limits and all. Those are the downsides if we try to choose. So it is basically very great for one-way push, like let's say dashboards, leaderboards, and AI token sending and all. And on reconnect, we'll have this like let's say somehow it disconnected between and all, so we'll have this last event ID stuff, which really helps us to replay from that event and make sure that client doesn't miss all of the events that it missed, even if it does disconnected and all. So that's server sent events. And now let's talk about the other one, WebSockets. So WebSockets is basically the go-to choice for our like true bidirectional communication between the client and server. So if we have like high frequency writes and reads, WebSockets is the one that we need to lean towards. So they basically what do? They build on top of this HTTP through an upgrade protocol, like which allows that existing TCP connection to change L7 protocols. That is this HTTP upgrade, and then both ways bidirectional between the client and server, and this basically stays open until closed, so we can send now strings, JSON, protobufs, binary, or anything. So the client now, how it connects, basically it initiates WebSocket handshake usually over HTTP, and then the connection will upgrade it to WebSocket protocol, and now this both client and server can send messages, and this will stay until closed and all. So That's the simple way to connect. And the challenges here is basically since this WebSocket is persistent connection, we need our infrastructure to support it. So that's where like we need to use the L4 load balancer. That is what really helps us to provide the infra that we need. And also how do we handle this churn connections, and also how do we maintain statefulness and all when we try to scale up and all, and how the deployment pattern is and all, and how do we connect the clients from the old servers to new servers and all. That's all the thing that we need to handle, because it gives us the advantages of what the functionality that we need, and also it comes up with this all of the operational challenges and all, and to think of these directions. So this basically those are the things that we need to deal with that. So like all the stateful connections and all, so need to rely using L4 load balancer and have this WebSocket server and whatever the driver service, and we have it and all. So this basically converts into proper reliable system. And so if we just terminate that WebSockets into dedicated service early itself, we can keep the rest of the system stateless. So now this WebSocket service can completely own connection state and scaling, and so that the whenever deployments changes also, there'll be just fewer churns and all those things. That's what balancing through this old and new connections and all. Those are the complexities that we need to understand a bit, and properly adopt this thing. And the other approach now is the WebRTC, which is the peer-to-peer. So this is the last option, and basically this enables direct peer-to-peer communication, like between browsers, and ideally these are perfect for our audio calls or video calls, video conferencing, and all those things. So here basically the idea is clients talk directly. So they talk directly in the sense, basically they talk to central signaling server, which basically keeps the track of which peers are available together with their connection information. So now once this client has the connection information for another peer, they try to establish a direct the connection without going through any intermediary servers. So in practice, basically no clients allow inbound connections to connect through directly for more or less security reasons and all. So that's where now how do we enable the connection between make it look between two clients directly. That's where we get the help from this two of these workarounds, which is the Stern server and the Turn server. So this Turn server, which is basically session travel utilities for NAT, is basically a protocol, and which basically allows these peers to establish these publicly routable addresses and ports, and we won't go into details and all, but it's the standard way to deal with this network address translation traversal. And basically it involves like creating open ports and sharing them via signaling server with peers. So this basically to talk between client A and client B, they need to go through this Stern server, and once this basically helps us to connect between them, and they can start talking to this. So if this Stern server fails, there's a workaround, maybe let's say organization restrictions or firewalls, and no matter whatever you use, it blocks and all. The turnaround is basically Turn server. So this is the traversal using relays around this network address translation. So basically again a way to bounce requests through this central server, which can be like now routed to this appropriate peer and all. So that's the flow. First trying to connect to signaling and then learn about the connection info for the other peers. And once we have that, we need to find this public address or ports through this stun server. And once it is done, we try to share the connection info between these peers, and then peers will connect to each other and share data and refresh info and all those things. So yeah, this signaling itself is real time, basically the channel here, nothing but it will be implemented using WebSockets or SSE. And then we use WebRTC for video or audio, and to offload this servers and all. So that's this WebRTC, like peer-to-peer communication thing. And that's the simple understanding of how it works, the process, the order and all, though not gone into depth discussion of the stun server and turn server, because they are itself have very deep discussion topics and all, and need to have a lot of systems knowledge over there. But that's the eye level understanding of the things that we need to do. And now we have seen a lot of the approaches for this step one that we have divided into. Now we need to understand basically which one to choose when and all those things. So these are the how do we decide. So we need to compare a very strategically and see which really makes sense for the system that we are designing. So let's see the protocol: simple poll, log poll, servers and events, WebSocket and WebRTC. So simple poll, it's a basically pull based model. So client will pull, and latency is basically high. Of course, we have the interval and all, and there's no dedicated infra that we need to handle. It works straight out of the HTTP. And here basically try to use this protocol when delay is okay, fine, I can wait for even if there is a delay and all. Now this long poll protocol, again this direction is client pull based, and the latency, it is not that high, not that low, medium, and there's no additional info is needed, and we can await a result for a bit and all. This is the way to go for. And the server sent events, it is a single way, one way from server to client, that's the direction, and latency is pretty low. And here the infra is basically trying to build on top of HTTP itself, the event source HTTP stream. And this is a one-way push whenever we need this leaderboards or AI chart tokens and all those things. That's the way. And WebSocket, it's a two-way bidirectional communication, that's the direction, and latency is of course very lowest. And here we need special infra WebSocket, and use basically whenever we need high frequency two-way. This is charting and those kind of applications. And WebRTC, it's a peer-to-peer direct client-to-client communication, and lowest latency. And here infra we need to have our own turn server, which is pretty complex to implement in real systems that we'll be having. And it's basically used for whenever you hear like video conferencing, audio or something like that, then WebRTC is the protocol that we need to adapt. So yeah, the ultimate logic is basically try to stick to the simplest that can meet our things, and then slowly think of upgrading from polling to SSE or WebSocket and those things. So this is how, like, the protocols that we can consider for our first point and all. Okay, so yeah, that's the decision. So question these things. So is the system that we are building, is it latency sensitive? If a straight answer is no, fine, then go for simplest implementation as long as it works, simple polling. If latency is sensitive, then again question, is it a frequent or bidirectional? If it's a no, then straight away upgrade it to server sent events. And if frequent and bidirectional, yes, again question, is it a peer-to-peer or audio or video conferencing or something like that? And if it's a no, strict no, the upgrade it to WebSocket. If it's a yes, go for WebRTC. So that's the lowest to highest complexity protocol that we can adopt for this step one. So yeah, that's start at the top basic, and then move on to try to upgrade as it can help make the system better. So that's the first hop, and that we can decide. And now let's talk about the second point, that is the server side push or pull, the second thing. So now how does this server learn about the updates from
our the sources, whatever it is. So again, so here we have basically kind of 3 patterns that we can try to achieve this step. So one is basically pull pulling, trying to pull via this polling. So what we do here, the server stores updates, and client will keep pulling it through polling and all. The other approach is pushing via this constant hashing. So here we'll talk about that. Idea is to like try to pin each user to a server, and the other approach pattern is basically trying to push via pub sub. So this is simple pattern of broadcasting through or topic bus and all. So let's see and elaborate each pattern at a time. So first thing is trying to pull with the simple polling. So here this is the simplest thing. What we do, basically we try to decouple the source from this client via this DB. So what we do now, we are trying to store all the state into this DB, and now whenever the client is trying to poll repeatedly, the server will query this DB and then give whatever the state it is to the client. So that's the simple pattern that we can at least think of. Simple polling, trying to pull. And so the advantage is basically this basically whatever the source we have, it will be updating the DB behind the scenes, and whenever it polls the server, it queries this DB and returns that. Okay, see the advantage is basically it's a dead simple to implement, and every state basically lives in the DB, and there is no special infra needed and all those things, and it doesn't even take much time to implement and all these things. The disadvantage is basically, of course, high latency, and also now excess DB load when updates are basically very infrequent, but the polling is very frequent, so there will be heavy load on the DB queryings and all those things. So that's the one thing one pattern that we can think of to achieve the second step. The other is basically pushing the via this now that was about the polling. Now it is the pushing thing. So here we need to understand we have two ways: pushing via the consistent hashes. So there is this thing. So we basically without even client asking, we try to push the updates to the clients, but we have a problem here, like if we directly choose simple pushing or so, because in many of the client update mechanisms that we normally try discussing, basically this long polling, SSE, WebSockets and all, the client basically we know that it has a persistent connection to only one server. So let's say user has connected to one server and user B is connected to server 2, or user C some server 3 and all those things. So they have a tied up to particular server, and that server will be responsible for sending the updates or something to client. That's the problem. So for example, let's take chat application or any of the scenario. Okay, so let's say now this user is connected to server 2, and now for us to send a message to user C, we need to know basically which server they are connected to. I know by default here we connected to server 2, and but how will we know that it is connected to server 2 and all? So ideally what we will do, basically we try to first figure out which server this user C has connected, and then we try to send that message to that server, and then with this server will look up like which WebSocket, SSE or long polling request is associated with this user C, and then this server will write then the message via that appropriate connection that it has. So this is the problem. So that is the pushing thing, and we have two ways to handle this. The first is basically try to use hashing. So that is basically the idea is like, how do we find the server to that specific user is connected, right? So first is hashing. So let's talk about the simple hashing, which is trying to like that's the like trying to connect to the right server. Idea is simple. We just try to use simple modulo operation to figure out which server that is responsible for given user. So we always try to hash a user, and among, let's say we have n servers, a modulus n will always pick the right server, and we know that that user should be connected to that server, and we know it is what the user should be connected to. So now to do this, basically we need to have a central service, maybe etcd, the one key value used in k8s and all, or zookeeper, to know like basically how many servers there are, which is in our case I'm assuming it's n, and then can assign them like each number 0 to n minus 1. So that is like which really helps us to manage this kind of all metadata, and now this allows the servers to keep the in sync as it basically updates on all those things. So now basically we make the servers count as responsible for this users to connect to service. Yeah, and that's the thing. So what happens now is basically, now when a client usually connects to random server, then this server, what it does, it uses this etcd or zookeeper, which is an orchestrator that we'll be trying to use to compute like which server is responsible for this the client, by hashing their user id or something and applying modulus n. Then this server, what happens, it redirects to the client to the right server, so and helps us to connect to this. Let's say it tries to connect to this, and it'll know that now after querying the zookeeper, this user has to connect to this server 2, and it will redirect the user to this server 2. So this way we'll ensure that it always goes to the right server that user is supposed to connect, and once that user is connected, then this server, what it does, it adds that client to map of connections that it has. So now we are ready to send updates and messages. Whenever we want to send messages to now to user C, we can simply now ask the user ID to figure out which server is responsible for them, and then we'll try to send the message to the server 2 directly and all. So that's the way, like connecting to random server, and it computes the actual server that user needs to connect to via this orchestrator, zookeeper or etcd, and then redirect that user to the right one. So that is the simple hashing thing, and the now this is a simple thing, like sending updates to right server to send to just a way to send a user A, we need to first hash to find the owning server, then it writes to that connection and all. So the one which I just discussed, and separate flow, if you wanted to, you can just try to check at that. Okay, fine. And there is another hashing which is called the consistent hashing and all. So the above simple hashing, the one which I mentioned, is great whenever we say like we have a fixed number of servers, and we are pretty sure like throughout this system we'll be having just 2 servers, 10 servers only, and then that really works. But let's say like we scale servers, we scale up, scale down, and all those things, and how do we deal with like which user needs to go to which user, and try to minimize the mapping of connections to like reassigning the users to servers and all. So that's the approach called the consistent hashing to help us deal with that kind of situation. So the idea is like make it look mapping servers and users onto as this ring. So and now each user basically goes to the, let's say user is somewhere here, and that user usually goes to the next server that comes in the clockwise direction, so it will be associated with the n2 server. And whenever now
we try to add a remove server. So only users in that section, let's say I try to remove this n2, and this users that they were associated with the n2, now they need to be remapped to the n3, and the rest of all the users that we have here, they just stay intact and no need to assign them. So this consistent hashing helps us with that. And same way, if I try to add here new server, only the users that are in this range needs to be remapped to this new server, and others just stays the same. So this is basically what it helps us with ideally. And but this is very complex, and because needs proper coordination and state maintenance and all those things. So yeah, this is basically we try to use when connections carry like heavy per user state, like for example, let's say Google Doc, so and all those things and all. So that's this consistent hashing. And yeah, this is just a removing server instance, like I am removing n8, so that is the thing. And now the only this users whatever it is should be remapped to this n1. That is the thing. So that is the pushing via the hashing, simple hashing and consistent hashing, the second pattern to try to meet the second point that we have tried to break into. The other is the pub sub, the pushing via a pub site, which is here what we do, we try to trigger updates using this broadcasting thing and all. So here we'll try to have a single service basically that will be responsible for collecting updates from the source, and then try to broadcast to all interested clients and all those things. So here popular options are basically Redis PubSub or Kafka and all. So this PubSub here I'm talking about, it becomes now the biggest source of state for our all real-time updates. So and our persistent connections are basically now made to this the lightweight servers, which basically simply subscribe to the relevant topics and all that we'll have in this PubSub, and then forward that updates whatever we have to appropriate clients to whichever the server it has connected to. So now when clients connect, so we don't need them to connect to specific endpoint server like we normally needed that in our consistent hashing which we just described above. And now instead it can connect to this server or this server, and once connected, basically that server, what it'll do, it will register the client with this PubSub the server, so that any updates now can be sent to them as well. Yeah, so that's the thing. Basically the client can connect to any endpoint server, and then that will register a subscription to that specific topic and all we have. So yeah, the now this endpoint servers are basically lightweight ones, and then the PubSub service like holds this topic, subscription, state and all those things and all. So message sending, this is how it looks like. Like like what we do, we try to basically publish to the topic, and the bus, whatever it is that we have, will try to broadcast it to subscribed servers, and then they forward it to the connections, whoever it is. So yeah, this subscribed servers receive the message, and then the servers will basically broadcast it to the connections and that we have. Yeah, simple, by just creating a topic, subscribing to it, and keeping a mapping from topics to connections associated with them, and that's the thing that we do. Same way, the updates and all, so this first, the one that I just specified, we publish the message to relevant topic, and then the subscribe servers receives the message and broadcast it to the user that I just mentioned. So the advantages of this is basically we can now use easy least connections load balancer to manage the traffic and all, and this efficiently broadcasting can be handled. And also now the state management is completely delegated to the PubSub, and it's completely lightweight servers and all. And yeah, and the problems with this, basically now Redis pops up, comes up with the like bottleneck into a design that we have. It can become single point of failure and all those things. But again, we can there are ways like Redis cluster and all, by default it'll have the backup and all, and it'll promote if it goes down and all those things. That's all sorted, but that's the good to know point if we choose this PubSub thing. So now the question is basically when to use what and all are the things. Basically any system that we'll be trying to design or something in our day-to-day work or just whatever it is, any interactive or live data is involved, then we know that this pattern is something that we need to implement. So try to question, maybe do updates need to feel immediate and all, then we know that it is just WebSockets or something that we need to adapt. Like WebSockets PubSub is something that's the most adopted thing, and then we need to decide where to use this properly or not in our system. So that's the simple thing that we need to identify proactively and see if this can be used and all. So in day-to-day basis, the common scenarios or the applications that is this pattern is applied is the chat related applications. So it's basically we try to in a group chat or whatever it is, we should publish the messages to all the users that they are part of that room. So we need to have this instant to all participants. That's where like WebSockets PubSub and ordering and presence and all those things comes into this pattern. And live commenting also, like millions at once, like fan out, and here we have this hierarchical aggregation and batching and all. That's all in separate discussion and all. You can check out the other video that I have. And this collaborative editing, that character level syncing, again here WebSockets plus CRDTs or operational transforms for conflicts and cursors and all. Live dashboards, a good way for SSC and gaming. WebRTC P2P, very highly adopted, and WebSockets to coordinate. Lowest latency is something that we need to guarantee. So these are like common scenarios. At least we can think of the adapting or the usage of this pattern that we can see. And also it's very important to understand when not to use as well. So if it's critically not at all latency sensitive system that we are building, then straight away not at all adapt this and just go with the polling thing. And because simplicity is something very highly appreciated in as long as we can achieve the functionality that we need for that business need and all. So simple polling is basically sometimes the best solution, and that is the thing. And now some of the scenarios or cases basically ideally that comes up is how do we deal with like failures or reconnection. So basically, let's say mobile connection drops and Wi-Fi drops out and server restarts and all. So we need to basically make sure that they reconnect super fast, so that we need to detect faster and reconnect without even any data loss. So so this WebSocket breaks can be very silent, and then that's the situation that we need to use heartbeats or pings to find out any dead connections, and then try to clean up on this missed beats and all for detecting. For recovering, so basically we need to track what each client received, and then per user queue or sequence numbers is something that we need to rely on. And then on reconnect, just we need to replay that gap based on the last event ID that per respective user has received, and make sure that nothing is missed. So detecting and recovering is very important. And the most used is basically Redis streams or something, like having proper backing for per user replay, like sequence numbers and missed message catch up on all those things. So this way, like we need to handle this reconnections and failures and make sure that no state is missed sending to particular user. And then the problem here, the hard problem, basic celebrity problem. So whenever the account posts having millions of users, they need updates simultaneously. So we need to properly handle this so that it will not break our system. So there is the concept hierarchical aggregations. So what we do here is we try to adapt fan in and fan out. So fan in is basically we try to aggregate the via this separate write process into the root processor, and which what this does basically, it tries to batch all of the things that is getting it from this write process and caches the updates and all at once. And once it has all of that, then we follow this fan out. So now we try to distribute to the users via this broadcast nodes that we have. Basically there will be regional servers where they try to pull from this root processor, and then they try to push it to respective local clients and all those things. So that is this the way, like hierarchical aggregation is something that we need to adapt to deal with this kind of situations. And how do we ensure that order of the messages is always preserved and all? That's also like the messages, let's say where it has like just milliseconds of difference between them. So how do we make sure that they're not in out of order and all those things? So assume like message 1 is at 0th time, message 2 at like 5 milliseconds difference, and now the arrays are reordered, so M2 then M1. So to handle those things, the there is like the vector locks or logical timestamps basically that we need to use to establish the ordering between these messages. And then now basically and try to usually recommended is to funnel through a single partition or single server for a total the order of the message that we send. So that's how like we try to deal with all of the situations and all. And overall this is the basically the real-time updates pattern and all. So yeah, like I said, this is the two problems. One is the client server protocol, and then the server side propagation. So idea is to basically always try to start simple, polling SSE, WebSocket and WebRTC only for media P2P, and then SSE simple rule, SSE for one way. If it's a one way, blindly use SSE, and if it's a two way, try to use WebSockets. And also like WebSockets also can be avoided if writes are less frequent, and we can do that through plain HTTP post request, and server side we can adopt the SSE. That way also we need to think through. And then the second the thing, propagating the updates to the server using the best everywhere adopted is a pops up, creating a topic, subscribing to it, and then broadcasting it to the clients and all. That's the pretty pattern in any of the systems. So by default try to stick that's a default. And other thing is basically connection, whenever connection state is heavy, consistent hashing is something preferred. So that's the real-time updates pattern. Hope you get the intent now and when to use and all. Yeah, all right, now let's talk about contention. So what is this dealing with contention mean? Here is basically this occurs whenever like multiple processes tries to compete for the same resource at the same time. Like let's say I'm trying to book the same movie ticket, or I'm trying to book the same F1 stadium that road ticket, or whatever it is, or like trying to bid for the same auction item or so. So without proper handling of this logs or anything, we get race condition. So this double bookings, and then inconsistent state and all, and a lot of problems as we try to scale. So how do we deal with this kind of problem is this pattern is all about. And so let's try to discuss on this the problem first. Let's try to understand here, and then we'll see the solutions approaches that we can think of. Okay, the problem here is the race condition. So let's take a simple example. Okay, assume like there's one seat left for F1 at Monaco. Okay, so the both Ellis and Bob want it. So what they do now, they try to hit buy now or something like that at the same instance. So the obvious way that we normally try to handle purchases basically
the one who reaches first will try to see that seat count 1 is left, and we'll check that if it's above 0, and then if it is, we decrement it and we'll sell the ticket. Okay, so if only one user is doing that exactly, then that's fine. But the trouble is basically when multiple users run it at the same moment, at the same instance, then Ali's first what he reads that one seat is available, and then let's say, like, after a fraction of millisecond, Bob is also like reading the same one seat is available, and in like before even so Alice has updated or something like that, and now Alice makes a payment, and he also makes a payment, and both see that the seat is Alice and seat is Bob's respectively, and at the end when they land upon the situation, both assume that that specific row belongs to them, but in the actual situation that's a duplicate thing. So the same seat has been booked twice by Alice and Bob. So how do we deal with this? So we have charged both of them a few bucks and allotted the same seat and all, and now definitely one of them has to be kicked out, and then something refund or something should happen and all those things. So that is the thing. Both get the confirmation for that specific row, and now there's a pure isolation problem and all. How do we deal with this? So that is this the contention pattern is all about. How do we deal all of this with the race conditions and all? So let's try to see. So there are the solutions that we can try to break it down. First is basically the single database coordination, and then if it's a distributed system, we have multiple shards and all. So let's see, like, how do we handle this contention. So if it's a single node 1 dB, there are ways, approaches that we can try to solve. The one is atomicity transaction, so trying to do all of this read, modify and write and everything in a single transaction, so that either all goes in or none of it goes in. The other is doing the pessimistic locking. So there's a for update, so the row that we are trying to read, so it will try to lock for that specific transaction, so other transaction will not be able to read it until it releases it. So that makes sure that only one transaction can do, and there'll be no double booking or something like that. So that is pessimistic locking. And there's isolation levels. We'll talk about that. What is, we have read committed, read uncommitted, serializable, and those things levels. I'll talk about what does that mean. And then optimistic concurrency, this is the concept of maintaining a versions and all, we'll talk. So these are like approaches if it's a single node thing that we need to handle these contentions. If it's a multiple node, so we have multiple shards and all, so there's a two-phase commit, and then distributed locks, and using Redis and TTL and other those things. And then Saga pattern, the compensation actors, like instead of relying on complete system, like making each step itself like rollable back to state 0 what it was. So that's the orchestrations, like temporal or something like that. We'll discuss on that. So here basically this is how we can try to break this down in these patterns. And the rule basically to deal mostly is try to keep this contented data in one database, so as to not complicate the system, but rarely that happens in real system because of the complexity of the business logic and the domains that we'll have to deal. Okay, let's discuss about first thing, the atomicity. So this is straightforward. The transaction, so basically we need to make sure happens in begin and commit thing, that read, modify, write cycle, that whatever we'll be having, so that either all goes through or else neither of them goes through. So that's the thing. So like idea, try to wrap in transaction, update that seats whatever we have whenever the available seat is greater than 0, and then insert it has been booked for that user and committed. That's how this happens. And so atomicity, that is what it guarantees. So no partial writes on crash or so, and it does not stop like two buyers reading like seats is one or so at once. So then the coordination is something that we need to handle across multiple buyers. So but at least this handles this all or nothing. And
even if seats are 0, it goes through, but just it doesn't throw an error, because the update matches zeros rows, and the insert still runs. That's what, like creating a ticket with no seat reserved or so, something like that. So that's one way to handle the contention. And let's see the second thing, which is the pessimistic locking. So here, let's say, like for example, if you're going for a movie or other concert or so, we all like try to go in a groups of 4 or so, something like we wanted to sit together as a family or friends or whatever it is. Now now not just the picking the seats alone is the factor. Now we have to read this seat map, like find 4 open seats in a row and only then claim them. So now that is funding the continuous block is a logic basically that runs in our application, and not just like now we can just right away rely on the where clause or something that we were trying to rely in the atomicity or so at a SQL level. So now the read and write can't collapse into a single statement or a transaction that we were trying to talk about. So assume like now two groups, they try to read the same map, like both land on the same row, A or B or whatever it is, and same 4 seat, and both try to go and claim it. So in the gap of like between the reading map and writing the claim, the other group can take seats, the ones which I usually picked up. So that is where like row locking is something comes in. So that is what we call pessimistic locking. So it basically prevents this conflict by acquiring this locks upfront. So this for update, what it does basically, clause locks every row, the select returns. So while we pick that specific section or so, we block that 4 tickets and then proceed till we release that in the transaction, whatever we do. So like that, other group will not be able to select or proceed with the same seat selections and all. So that's what, like, so assume like we have 3 threads trying to hit the same database row at the same time. So if we had this pessimistic locking applied, so first the thread 1 holds that lock, and the other threads which were trying to access T2 and T3, they wait, and once now as time progresses, T1 it's done booking, or like some other reasons it booked or not booked, that thread 1 releases, and now this T2 will hold that the same rows or the whatever the rows the user picks. And like this, this is how we try to handle this pessimistic locking, so that there's no conflict and all. So yeah, and this for update is super helpful for serializing access, and also like additional conditional logic checks, and make sure like if it's something related to seats, we always do available seats greater than 0 to enforce that, and also like so that not just relying on this locking but also on the conditional stuff that we have. So this is again one way to handle this race things that we see. And then let's try to understand the isolation levels here. So by default, depending upon the database that we're using, there are standard isolation level that will be there for transaction. So imagine like for example, sometimes like let's say like 2 transactions trying to read an overlapping set of rows, like each makes some updates or whatever decision that is valid on its own, and it updates. And but when we consider 2 transactions as one together, then that is something not valid. So since no single row collides, and that each individual transaction passes, the row lock or version check and all those things will really not help. So that is what we call this as a right skew or something like this. So picture a situation or something like that, where I'm trying to go on a leave, like we have 2 engineers or so and trying to go on a leave, and one is available and one can go leave is something. The condition is like at least one engineer has to be there to support the product or whatever it is thing, and we have 2 engineers, and one engineer will think like he'll check the schedule and see that other engineer is already on the call and try to remove that schedule from his calendar, and the other engineer also does the same thing. Now no one ends up being there to support the product and all. So because they are completely different rows, one engineer, 2 engineers are different rows, and on their own there's no shared row to lock version or guard like with the where clause and all those things. So that is where so this transactions, if we have by default this read committed, these transactions can happen in any order, so independently and all, and there is no serialized and all. So the hardest, strongest isolation that we can guarantee if we use this serializable isolation level. So this basically what it makes, now every transaction it guarantees that only one transaction will run at a time, and it will be like properly in the serialized order. So now whenever I'm trying to do this, now the 2 engineers check which I just mentioned, so it will always check if the one engineer is if engineer count is greater than 1 on that particular day or not, and it prevents the latter's engineer's request, and it will keep it will deny that request, and it will keep that engineer for the product and all. So that's the thing. So this is the strongest one. So we by default will have read uncommitted, which is basically we can see uncommitted changes from other transactions. That is rarely used at all. Read committed is basically a default in PostgreSQL. So basically we see the changes which has been committed, and repeatable read is same data will be read multiple times within a transaction. Basically it stays consistent. And serializable, the one which I was talking about, is strongest isolation that it guarantees, but again it comes with a cost, meaning it needs to track all the reads and writes it to find these conflicts, and every abort like throws away work has to be redone and all. So it's a most expensive option that we have, and it has to be chosen only if we cannot deal the problem with first the pessimistic lock, and the other approach which is optimistic concurrency control, which I'll talk about, and this should be the last preference for us. Okay, and yeah, that's the isolation levels and the single node that we can consider. And then this optimistic concurrency control, so here it's idea is simple. We assume that all conflicts are rare, and they hardly will collide and all, and what we do here, we just try to maintain this version number such that it will be unique as per our that domain or business logic that we have. So every time we do that operation, we try to update or increment that version so that if others while he was trying to read, if it's different to when he's trying to update, then it'll just abort in that transaction and all. So simple example, he's trying to update when version is 42, so row is updated and version now we try to increment it to 43, and Bob he's also trying to do at the same time of 42, and he has updated this. Now when he's trying to update, he'll see the version has changed, so this will be rolled back and all. So like this, if we try to maintain this version number, and that's the where condition check, it's properly will be helping us to avoid this duplicate race conditions and all those things. So that's the one of the concurrency control way to handle this contention thing, version 1. And now talking about the multiple nodes. So single nodes, those are the approaches that we can deal with. So this multiple nodes, First thing is a two-phase commit. So two-phase commit is straightforward. So we'll have one coordinator, which is the coordinator server. That is what helps us in driving the all or nothing commit across the DBs, whatever the shards that we have. So here basically it helps us to prepare and double check if it's prepared or not, and then commit and committed and all. So this way we'll have in the phases wise, and we'll try to handle. And even like let's say between prepared and commit, if it has crashed, so then we can basically use this log to enable that recovery and then preserve that consistency, and though the availability might be sacrificed, but make sure that the eventual consistency at least is guaranteed. So that's the two-phase commit, one of the approach that we can think of. I know I'm just trying to do it cover it at high level, but that's one approach. The other is basically think of this distributed logs. So now when one process involves like touching a resource, like many processes are trying to touch the resources at a time, then we need to make sure that only one process can touch the resource, that one. So that is like we try to log that. So the idea is basically handle this with the maybe adding some time to live on that specific data, or instead of now dealing with that database rows and all, so that that can be only used by that transaction and all. So this ideally is implemented using Redis plus TTL, and this database columns status plus expire set, and so that no one can pick it up. And if it's a like also we can use etcd as zookeeper to handle this distributed logs and all. So yeah, same logging idea like we just discussed on single nodes. So again, let's say I pick one seat, some like seat 15th seat number, and the app should help us to hold that for 10 minutes, like while we try to fill out other details and payment details and all. If our update whatever pessimistic log we just mentioned, it really can't help us basically because it's not just the row, the payment and other details and all the steps and all, it's separate from the systems and all. So here what we need to now basically is instead of holding the log as a transaction, we need to start holding it as a data. So like basically a record like who is holding a seat, and like when their hold expires and all. So like trying to set the TTL on that user or something, like 10 minutes or so, and then after 10 minutes we can just release that, and the other users can claim it. So mostly these atomic operations are handled using this Redis and TTL, so which makes it basically greater. So basically we don't have to manually remove that logs after TTL has met 10 minutes or so. It will by default clear that, and will be able to use by other users and all. And and that's what one thing. So using set nx, like only set if it not exist, and that thing. And database columns by default, just we can use columns like reserved by and reserved until and all, and then do a check whenever we're trying to update, like if reserved until is less than the current time and all, only then allow this updates and all those things. Okay, and we have like dedicated things in the distributed system, zookeeper, etcd, like coordination services, where they provide strong consistency like guarantees even during network partitions and leader failures. So this basically they use ephemeral nodes that will automatically disappear when the client session ends and all. So those nodes, so providing natural cleanup for that crash process. And now both systems will use consensus algorithms, for example raft for etcd and zap for the zookeeper, to maintain the consistency across multiple nodes and all. So Here the advantage is basically we can handle complex failure scenarios that the Redis and the database ideally struggle with. And disadvantage is basically operational complexity. We need to run and maintain separate coordination cluster, and then holding the seat in reserved state like this is a much user experience thing. And now it also like shrinks the window like where two people can fight over the seat from the old checkout down to like instant of selection. So nobody fills out the payment only to be sold that seat is gone and all those things. So every situation is something we need to handle and make sure that the one whichever we can adapt and make it better user experience is something we should try to go for. Okay, so yeah, and also there's a saga pattern. So instead of trying to do the global lock on all this series of steps that can happen in the particular flow, like we need to make each step can commit on its own. So like, and each step can be undoed with the compensations on failure and all those things. So that's the orchestrator, ideally temporal or cadence. So they help us to track progress, and we can resume after crash from that committed step and all using the replaying from the HTTP that we have and all. So take an example of like we debit the ls and committed, and step 2 now done, and then we credit to other account, and then step 3 we send confirmation. So even if something is failed, we can roll back to previous steps and all, like to compensate. Like we should have the similar logic to compensate the same, like to refund back and all to respective accounts. So I'm just trying to state an example here to transfer amount from one account to another, but that's the saga pattern is something that also we can try to see to skip the global lock and all those things. Okay, so now ideally that's the thing. And I know I rushed a bit and gave you just overview and did not give you high level like in detail things on distributed locks and all, especially on etcd or zookeeper or something, but it comes with practice. So just try to dig it on your own self, and just the intention is to just to give you an overview on high level direction of what approaches that we can think. Now let's see like when to decide which approach. So first we need to always try to keep it in single db. So if single db fits all data, then straight away go for that. And now how much contention is there? If it's very very high, so we'll always choose transaction plus pessimistic locking, so that this will help us to resolve any race conditions and all. So if low, then we just prefer this transaction, and then this optimistic concurrency control, just add these versions, and then proper things like resolved by resolved until, those kind of checks, version numbers and all those things, so that again contention can be easily handled. And if it cannot fit in the single data, then can we tolerate eventual consistency or not, which is something we need to question ourselves on. If it's yes, then we can go for saga pattern, use the commit level steps where with compensation actors and all, so that each commit can be undone. So like temporal steps and all. If there's something that we cannot tolerate eventual consistency, go for two-phase commit coordination server and all. So that's how like choosing the right approach. So now let's try to see the comparisons between all the approaches that we have for single node as well as the multiple nodes. So pessimistic lock, so we try to use whenever we have an high contention, and like avoid strictly when there's low or raise chances of race conditions and all those things. And latency is low, and complexity is also low. Serializable, like we should try to use when we can auto detect, and just avoid this basically when performance is very critical, because this is very expensive, because it needs to read through all writes and reads of the log, and then try to construct the series of transactions that happen. And again latency is high, so try to avoid. And again the complexity is low, you just need to set the transaction isolation level to serializable. And this OCC, optimistic concurrency control, use when there is low contention, and then avoid basically when we can't retry, and this pretty standard. And distributed transactions basically make the transactions as atomic, and avoid basically when we need high availability and all. And distributed locks, user reservations, especially tickets or other stuffs. And yeah, and then depending upon the complexity of the tech involved and all, we need to avoid those conditions. Just the high level comparison that I'm trying to lay out. And now when to use this pattern is basically we need to spot this race conditions possibilities, and see if there is any signal, like if there are any logic or somewhere like it's trying to compete for the limited resources, like concert tickets, auctions, like any flash sale is happening, driver matching. And so that basically anything related to booking, charging, payments like seat reservations, room scheduling, then consistency, basically balance updates, inventory, collaborative editing and all. Then this same op if it fires on many servers, and then sequence of the order matters and all. So if those are all the signals that you can see, like then the contentions approaches that we just discussed of single node and multi node, something that has to be triggered, and then see if we can use any of this to prevent all of these conditions that we have. So that's the the pattern, at least the signals, to see if these approaches can be adopted. The common scenarios in the systems that we normally see is basically in our online actions, this optimistic concurrency controls, like we always try to set the version as the high bid, highest thing, so that only we try to create new bid only if it matches or greater than that number. Okay, so that's the thing. And like any booking systems, this distributed lock reservations like Redis plus TTL is what we use, like ideally blocking that seat for 10 minutes or so. And coming to payments or banking, strictly using Saga pattern or 2PC two-phase comment, so if strict consistency is needed. Ride sharing dispatching thing, trying to add this TTL cleanup and then pending request status checks, again OCC thing. And flash sale and inventory as well, do the version column checks and the cart holds or not, and for reviewing also like dedicated version column and all. So these are the situations, at least these are the systems that is commonly we see this contention problems, and then approaches to which approaches to take to deal with it. Okay, and when not to use or overcomplicate, basically trying to reach for distributed logs like Redis and this etcd or Zookeeper, when like we can do it in single DB transaction with row locking or OCC, is something we should avoid. And so for example, product descriptions, low contention, there's a very less possibility of race conditions, so just strictly avoid. And single user operations and read heavy workloads, there's no writes and all. And this is just the situation, just try to avoid of not adopting this pattern at all, because there's no chance for us to see the race condition or single things trying to compete for multiple resources. And so in the couple of like scenarios things, let's say like true transactions tries to grab the same row in the opposite order and they wait forever, like for example there's a chance that if we have no consistent ordering in the resources that user is trying to select, then there'll be deadlock. So what we need to do, ideally we need to, whenever we are returning some seats or other stuff, we should always be sorting it by something deterministic key, like for example sorting by user ID or so that we can log the lowest first, and regardless of who initiated and all. So that way like this deadlock is something we can avoid. So that's very important thing. And then if the coordinator crashes in the two-phase commits after this prepare things, then the participants set holding logs and all. So how do we deal with this is basically trying to rely on this log to finish the in-flight transactions, and then proceed picking the next one. So just trying to handle using this log recovery mechanisms and all. And then this ABA problem. So let's say if A value goes to A, and from A to B, B to A, and so how do we deal with this? So for example, let's say a restaurant's average rating is 4 and we have 100 reviews. So review A 5 stars, so it reads 4, and review B 3 stars, it's read 4. So now here how do we deal is here we can now use the rating as the basically if we just try to use rating as the version, it fails. So in this situation you see the difference now. So both rights see this 4, and so one review is ideally will be dropped, and then review count will be wrong. So in that situation, how do we deal is basically we need to have dedicated version column that basically bumps on every right of the review. So and then we try to update and set this average to 4.1 and update review count and version we increment. So and do that. So basically try to use the composite keys when there's a chance this single key can still help us put us in the racing problem. So okay, that's the thing. And then the art partition and queue thing. So again, if everybody is trying to compete for the same resource and hammering one resource, how do we handle that? So that's what we just need to split one item into 10 separate actions and add some message queue. So order writes and then handle one at a time and do whatever they work and try to do it pass it into the DB. So these are like few of the situations we need to deal with. Mostly the problem is just the pessimistic locking, and then this optimistic concurrency control with version number and other composite key just doing this checks, and then Redis and TTL distributed logs should do the job in most of the situation in any of the system. And that's it. This what the contention pattern is about, and just try to stick to single database as long as you can, and then solve this problem simply with the single node approaches that we discussed. And then whenever we have distributed things, think of 2PC sagas logs, like when we have really outgrown the operation of not hosting single database. And then yeah, that's the thing. This is what the contention pattern is all about.